for about 20 minutes and leave about 10 minutes for Q&A. So that's a task for all of you to come up with good questions for them at the end of their talks. And first up is Mr. Fujiwara from JPRS. We'll talk about negative caching. So. Does this already work? Yeah. Oh, but just for laser pointer. So I have to use this for this. Okay. Yeah. Okay.
Thank you. Hello, I'm Kazunori Fujiwara from JPRS. Today I will talk about a countermeasure of random subdomain attacks, aggressive negative caching with NSEC. This is overview of random subdomain attacks, referred as water torture attacks. Random subdomain attacks send many non-existent name queries to full resolvers. Their query names consist of random prefixes and a target domain name. And effects of the attack are as follows. Negative caching of the target full resolver doesn't work well. The target full resolver sends queries to authoritative DNS servers of the target domain name. As a result, outstanding queue of the target full resolver overflows and the full resolver will drop queries from both users and attackers. This is overview of random subdomain attacks. Attacker sends queries to customers' CPE, which acts as open resolvers, and then CPE forwards queries to full resolvers, customer-only full resolvers. And full resolvers send queries to authoritative DNS servers, and number one, negative cache doesn't work well, and number two, these authoritative queries are very large number. And as a result, the full resolver's outstanding queue overflows, and then the full resolver drop customers and attackers' queries. And then I made a performance evaluation tool for random subdomain attacks. This is very small C program which generates query packet and periodically send queries to one IP address. The tool sends queries to specified IP version for address periodically, specified by argument, and query names are specified domain name by argument with random prefixes. %C, 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 %08D. And this is usage. Random prefix evaluation, IP version for address, domain name, queue type by number, weight by second, duration by second, receive weight by second. The tool analyzes all cores of response packets. It can send approximately 10,000 to 20,000 queries per second. And this is my test environment. I prepared 3 VMs, 2.5 GHz CPU, 4-core, 4 GB memory VMs. And one runs evaluation tool, and the other runs binary or unbound full resolver, and the other is authoritative for signed DNS Lab JP, and I used signed DNS Lab JP as a target domain name. And before experiments, I performed dig at mark target full resolver signed DNS Lab JP SOA to cache DNS Lab JP signed DNS Lab JP information. And this is one typical experiment. This is the experiment common data. The command is random prefix evaluation, target full resolver address, signed DNS WJP 1 shows A and 0.0001 125. This means 10,000 query per second, 120 seconds, and which generates this generates 1,200,000 queries. And I show results using 4 data. Measuring CPU usage using topo command looked by me, and I performed dig command under evaluation. Dig at MAC target 3 domain names. And I captured and then I logged the count of received responses. Lost queries, RCO2 subfail queries, RCO3 NX domain name error queries, and I captured all packets which the full resolver send and receive. And I passed and counted number of queries to authoritative servers, signed DNS LabJP, DNS LabJP, JP root. This is one typical experiment. Target full resolver is bind 9.10.2. Named CPU usage becomes about 330%. This is very high because current number of CPUs is 4. And the named responds 99.7% RCO2 subfail responses and 0.2% name error NX domain responses. And there are 536 no error. And the full resolver by 9 sends 600,000 queries to signed DNS LabJP authoritative DNS servers. This number is 50% of received queries. And queries to other authoritative servers are very small number. Root 50, JP17, DNS LabJP 4. And this table shows experiment result for experiment result of bind 9. Bind 9 works well under 1,000 query per second attacks. Very small CPU usage both without DNSSEC variation and with DNSSEC variation 84% CPU usage. And all answers and by 9 response, NX domain RCO3 100% name error responses. However, by 9 sends the same number of queries as received queries to authoritative servers. 99.8%, very high rate. And by 9 answers subfail under 10,000 query per second attacks. (10,000 query per second attack case, by 9 response 99.7% subfail and 0.2% name error. With the DNS validation case, by 9 answers 97.8% subfail responses. And by 9 sends over half number of queries as received queries to authoritative servers, even if it responds subfail. By 9 full resolver sends 600,000 queries to signed DNS LabJP authoritative servers. Very high number of packets. This table shows experimental result for unbound. ITC unbound 1.5.2. And unbound works well under 1,000 query per second attacks. And unbound sends 1.5 times of queries as received queries to authoritative servers. It is larger than bind9. And unbound drops 73% of queries under 10,000 query per second attacks. Unbound sends about a half number of queries as received queries to authoritative server, even if it drops, it doesn't respond. And both bind9 and unbound doesn't send small number of queries to root, JP, DNS Lab JP, authoritative servers. And this is summary of experiment result. Bind9 and unbound work under 1,000 query per second attacks on conventional hardware. However, they send the same or 1.5 times of queries to authoritative DNS servers. And neither bind9 and nor unbound works well under 10,000 query per second attacks. And half of queries of received queries are sent to the authoritative DNS servers in a worse thing. As a result, easy to DOS. Then, as a result of the experiment, Akira Kato and I proposed an internet draft. And the next 7 slides are quotation from ITF slides. Draft visual DNS of NSEC aggressive use 00. And if target domain name is signed, target full resolver receives NSEC3 resource records. Each NSEC URL contains range which include query name, and NSEC URLs are signed. NSEC URLs are cached. For example, target domain name is example.com. If a.example.com in NSEC www.example.com is in the cache, there is no domain name between a.example.com and www.example.com, and need to check existence of wildcard. However, section 4.5 of RFC 4035 defines, in theory, a resolver could use wildcards or NSEC URLs to generate positive and negative responses until the TTL or signatures on the records in question expire. However, it seems prudent for resolvers to avoid blocking new authoritative data or synthesizing new data on their own. Resolvers that follow this recommendation will have a more consistent view of the namespace. Then we can generate a negative response from the cached NSEC URLs. This document proposes to relax the sentence, but the block doesn't prohibit, I think. And this is aggressive use, an idea of aggressive use of NSEC3. When the query name has a matching NSEC or NSEC3 resource records in the cache and there is no wildcard in the zone, which the query name belongs to, a full resolver is allowed to respond with NX domain error immediately. The matching procedure may be applied to all ancestor domain names of the query name, and need to check existence of wildcard in the zone. And there are side effects. Aggressive use of NSEC3 resource records may decrease queries to root DNS servers. People may generate many typos and they tend to generate DNS queries. Some implementations leak non-exist TLD queries whose second-level domain name are different to each other. Well-observed TLDs are .local and .belkin. With this proposal, it is possible to return NX domain to such queries without further DNS recursive resolution process. It may reduce round trip time as well as reduces the DNS queries to corresponding authoritative servers, including root DNS servers. And there are considerations. Newly registered resource records may not be used immediately. However, choosing suitable TTL value will mitigate the problem, and it is not a security problem. And there are implementations, I think. This technique is called as NSEC-NSEC3 aggressive negative caching in unbound to-do file. And unbound has aggressive negative caching code in its DLV validator. And I implemented NSEC aggressive caching using unbound and its DLV validator code. And after then, IT part was finished, and I evaluated my patch. Unbound has NSEC aggressive caching code in its DLV validator, and I implemented NSEC aggressive caching to Unbound from its DLV validator code. And my patch is here, and the patch works with both Unbound 1.4.22 and 1.5.2. And there are limitations. R-code 3 name error answer doesn't contain authority section because SOA synthesis is hard for me and it is not tested well. I used the patch, but current user is only me, and it doesn't support NSEC3 yet because Unbound code doesn't support NSEC3 now. And this is test results for Unbound, patch to Unbound. Patch to Unbound works well under 25,000 query per second attacks with 0.3% loss. And the full resolver sends a small number of queries to authoritative DNS servers. This part. In my idea, this query becomes 10 or a small number, but it is many, I think. And this table shows comparison under 10,000 query per second attacks. Neither bind9 nor Unbound works well under 10,000 query per second attacks, and aggressive negative caching solves the problem. However, the patch doesn't work perfectly because it still sends a certain level of queries to signed DNS lab JP. And I had another implementation. Google Public DNS implemented, and I heard from Sebastian Castro this March, and I tested it and I agreed without any records, sorry. And then I tested Google Public DNS address to make this slide. Then this May 6, and I generate 10 query per second, 120 seconds, 10 query per second, 120 second queries, and then I got 3 surface and 99.75% name error, and Google address generate 1,041 authoritative queries. The attack succeed, and they don't implement now, I think. And conclusion. DNSSEC is aggressive negative caching is a countermeasure of random subdomain attacks, and implementation is not so hard. RFC 4035 doesn't prohibit the use of the use of NSEC in the cache, I think. And this is my future works. I need to update draft to add algorithms, ideas. And I need to contact FluResolver developers. And if possible, I would like to develop new FluResolver. And that's all.
So there's a mic in the middle. If you have questions or comments, please find your way to the mic. And don't forget, of course, to state your name.
So, Warren Kamari, one quick question, I might have missed it. Did you provide your patches to Unbound and ISC?
Currently, no. And I would like to contact.
And this looks really cool, by the way.
Stefan Bartsmeyer, AFNIC. In the random QNAMES attack, there is very often a fixed suffix, such as DAFA8A.wf. So you could have negative caching in the resolver on protection, even without DNSSEC, if the resolver accepts to cache the whole tree, not just the name, but the whole tree, something which is currently limit, because if you do so, you have a problem with name servers like Akamai who send back NX domain when there is an empty non-terminal. But if you follow the tree-like structure of the DNS, once you have seen that there is an NX domain for the suffix, the resolver can send back NX domain immediately for every name under the suffix. This is something that resolvers don't do today, but if they do it, it could complement your solution for non-DNSSEC domains. What do you think about it? It was suggested in a draft which is now expired, a draft by Neves and Vixie and someone else a few years ago.
Without DNS validation?
Excuse me?
The zone isn't signed case.
No, what I was talking about was something which works for non-signed zones, zones which are not signed, and if the attack use a fixed prefix, a fixed suffix, something which is quite common today, but may not be the case forever. But today, typically, the random QNAME is suffixed by something like SLD on TLD, and often www.sld.tld. So once you have seen once a resolver receives the first NX domain, it could generate the further NX domain without going back to the authoritative name servers. It works because the DNS is hierarchical. But today, resolvers don't do it because they are afraid of broken name servers like Akamai, who send back NX domain for empty non-terminals. They shouldn't, but they do. So there is an interesting problem. Should we use this possibility to protect against a random QNAMES attack, even if it breaks some broken name servers?
With a DNS, not signed zone case, it is hard to consider the general countermeasure. So my proposal is limited to signed zone. Thank you.
Hey, Ed Lewis, Fujiwara-san, your work is always very interesting. I can go on for hours about what you're talking about, but I'll try to be short. There are two things in your talk that stand out. One is attacks, right? And we talk about attacks all the time and how to respond to them. And I think it's very important. The first thing we talked about how the CPEs are being used to launch these attacks. It's very important. And your response to this is to counter that. But your response, which is the second part of this, is telling a recursive server to start making authoritative server decisions. What doesn't exist? And I remember back when we wrote that paragraph about whether or not a recursive server could be aggressive in this way. The reason why it welcomed wholeheartedly was that we didn't want the recursive servers to usurp the authoritative servers' abilities there. And again, it's if they create new names, names pop up, you're denying that they exist, is what's happening in this. I think that what you're looking at, I think it actually makes sense to be aggressive. I mean, because in the protocol, we have caching, we have a time lag. I think all concerns about names popping up and not being seen right away, we just can't deal with that. The protocol is already very slow to respond to changes. If I told you as an authoritative server, here's negative information, TTL is an hour, you're going to use that for an hour. And how you use it, it should be valid no matter whether it's for that name or what it's telling me. So I think there's actually a good reason to go ahead and say, yes, we should actually be aggressive in doing this. What I want to add too is that for NSEC, this works pretty clearly, because in NSEC, I tell you from here to here, there's nothing. You can trust me for an hour, I'm the authority, and you can go off and do that. For NSEC 3, I don't think it will be successful. I may be wrong about this, but NSEC 3 collapses the zone structure in such a way that you can't tell where the other empty non-terminals are, for example. So I don't know that NSEC 3 will be able to do this. I think that this will definitely work for NSEC. Now, going back to the first comment about the attacks, this is a good idea. It's promising and showing some results. Make sure that when we do this, though, we don't burn into the protocol's architecture implementation something permanently for attacks which we know over time change, shift, and evade the defenses. And that's what I'm thinking when I hear the presentation in two parts is it's here for this problem that may or may not stay, and here's a permanent way of doing things, which might be a good idea anyway. But the NSEC 3 thing kind of gives me some pause because I don't think this is generalizable into the NSEC 3 or any other negative answers that try to hide the structure of the zone.
Thank you. NSEC 3, I need to add text about NSEC 3, I think. Thank you.
So the NSEC 3 also was a bit something that was interesting to me, but as I understand, there's no answer on that yet. It, of course, only works for assigned zones. And then for NSEC 3, I mean, we have the opt-out problem that will appear there because a lot of the people use opt-out to actually hide the large portion of their zone that are currently not signed. One remark on your testing. I mean, I've done also testing with various resolvers on random subdomains, and 10,000 QPS to me seems to be something that everybody can digest these days. So what kind of recursive context did you use on that? What is the amount of recursive context? Because I don't think that 10,000 QPS will overload a modern resolver.
Pardon?
In the configuration of unbound or bind, how many threads, how many recursive contexts did you use? Because they must have been pretty low, or?
Oh, my experiment, bind 9 default and unbound default, and only four CPUs in one VM.
So 4 threads.
Yeah, bind 9 case 4 threads, and unbound case 1 thread, I think.
Okay, so default configuration. Okay.
Yes.
I mean, in real life, you should up these numbers considerably because your first defense against these attacks also is whatever you can recurse out. If you have multiple thousands of recursive contexts, these results would have not been quite different.
Yes, thank you.
All right, thank you very much.
Thank you.
Next up, Mr. Langerholm from Microsoft. Are you presenting alone, or are you having you have a co-presenter? Okay, so you're going to tag team it a little bit.
Good afternoon, everybody. My name is Stefan Lagerholm from Microsoft. I'm here with my bald colleague from Microsoft, Joe Rosselli, and even the stock photo that we found in our presentation doesn't have much hair. So anyway, we're going to talk about negative caching of DNS records today. And I'm going to go through a little bit of the background and the problem statement and look at the RFC that specifies negative caching. And then I'm going to hand over to Joe we've been running some experiments, so he's been running some experiments. So we go through some of those results and then open up for some conclusion and discussion at the end. So we realized the hard way, you can say, that we need to better understand how long a negative cached record can be found on the internet. So the use scenario is that you have a zone, you have something in that zone that you want to have in there, but for some reason you remove it, and then you realize you made a mistake, you want to put it back, right? So how long do we expect it to take before that record shows up again? Similar to Dwayne Wessels, and I realize I think I misspelled your last name there, sorry for that, but you had a similar presentation in Phoenix at OARC about 2 years ago. An open resolver's view of the New York Times, very bad day. So New York Times, they had more of a positive cache issue, right, where some hacker went into the registry and changed their DNS servers, and then they changed it back, and it took a while for the internet to time out. And Dwayne did a nice presentation with a lot of graphs. We're not going to have as many graphs today, but it's similar. But we're not talking about normal caching in this presentation at all. We're only talking about negative caching. And we're not talking about serve fail caching or any other type of caching that can exist. So we're just focusing on the negative caching issue here. And we're looking both at authoritative servers and recursive servers in those experiments. And, so really the question we wanted to answer is how long will the lack of a DNS record be cached on the internet? But then really the first, when we looked from a helicopter view on this problem, is negative caching really an effective method of improving the DNS experience, right? That's what we need to ask ourselves. Why are we even doing this? And then, we tried to figure out what kind of experiments do we need to do to better understand this problem. And going back to the, improving DNS experience, when we talk about negative caching, we have two groups of operators and users that benefit from negative caching potentially. The end user, who really doesn't care about the number of queries, he's not sending a ton of queries, and the end user wants to have the most recent data. If a record is supposed to be there because somebody published it, the end user wants to have that record as fast as possible. So from an end user perspective, essentially turning off negative caching would be the best. But there's competing interests, certainly, that from a DNS infrastructure operator, we want to limit the query load. So negative caching potentially could be a good way of doing that. So we need to dial in here between the end user and the infrastructure operator and try to find a good middle ground for where to put the negative caching TTLs. And as I guess everybody knows in here, there's in the SOA record, the fifth number there, 3,600 in this case, referred to as the minimum TTL, is the TTL that should be used for negative caching. And the SOA record should be included in any responses, both for NX domain and for empty no error. So the idea is that when an authoritative server gets a query where there is no record, it's going to insert the SOA record and send that back, both for NX domain and for empty no errors. There's interesting that some systems out there, they're actually sending different, depending if you generate an NX domain or if you generate an empty no error response. The TTL is different, or the SOA TTL is different. So they have logic to differentiate between an NX domain and an empty no error. And for the reminder of this presentation, just to not confuse, we're trying to use the term negative TTL here for the TTL that's returned in the SOA record. So looking at RFC 2308, which was written by Mark Andrews in 98 or 99, somewhere around there. So it's a good 15 years old. There's three sections that I want to highlight here. Section 4 really just defines the meaning of this setting, that it is to be used for negative responses, the SOA minimum field. And then section 3, it goes into the logic. So here's where it sets what authoritative servers should do, right? So this is kind of important for this presentation. The authoritative server should set the SOA TTL to the minimum of the minimum field of the SOA record and the TTL of the SOA itself. So if I go back to the example here, the minimum of the SOA TTL and the minimum field is the lowest, in this case, 3,600. So that's what you should set as your SOA TTL when you send back the record as an authoritative server. And then section 5 talks about what the caching of negative answers, and essentially you take what the authoritative server have set in the SOA TTL, and that's what you're going to use for and to determine how long you can cache this record in your cache. So that's the RFC. Looking at the default TTLs here, it's a pretty large variation. I took the kind of top 4 from what I know, what I think would be the most used recursive servers there. And there's a factor of almost 100 here between what the Windows DNS server is using and what, for example, Unbound is using a full day. Looking at the RFC, there is a recommendation in there, even though there's a spelling error in that recommendation that I fixed in my quote here. But values of 1 to 3 hours have been found to work well and would make a sensible default. So, and I think, to be honest, when looking into this, I think 1 day I think is a little bit too high. 3 hours maybe also. I think this was written 15 years ago. We're more an interactive internet today where people expect stuff to work, and you spin up high priority calls if something doesn't work and so on. So I think it makes sense to have a lower TTL, max TTL today. Then what we did next was we started to test, and we tested the Windows DNS server, bind, and unbound, and the idea was to let's iterate through the Alexa top 1000 or something like that to see what we can find, just to see how different servers are behaving. And we didn't get far, as you can see here. We just get to the Alexa top 1, and we stopped there and we scratched our head and said, this is kind of strange. We had 3 different responses here. So the Microsoft DNS server responds with 300, the bind responds with 60, and unbound responds with 600. So very strange. And to give you an explanation here, bind is doing the right thing and is responding as intended from Google. There's some room for improvement on the Microsoft side, where we actually take the negative TTL, the minimum TTL, and copy that over on the recursive side as well. And then Unbound has an interesting, I call it a domain-wide negative caching. So, and this, if you want to reproduce the Unbound, you need to have IPv6 enabled, and you need to have a cold cache to reproduce this. So what's happening essentially is that during the resolution here, it goes out and asks for a quad A record and gets an empty no error, which does have the 600-second TTL, not the 60 TTL. And it's using that domain wide for anything related to that domain. So the actual record we asked for, even though the TTL was 60 on that, it uses the 600. So here's an example how, on a few different recursive DNS server, you can actually see higher TTL than was what intended from the authoritative server. So we realized we got to do some more experiments and see how bad is it, and how what can we do to improve it, and see if we can come up with some results. So with that, I'm going to hand over to Joe to cover some of the experiments that we did.
Thank you, Stefan. Thank you all for having me here. This is great to talk about. This is a really interesting topic as we dove into it. So ran a bunch of tests, really, just to see how the negative TTL works in real life. first set of tests were against authoritative servers, so just looking at the authoritative side. Then next set of tests were to gauge what was happening on the recursive side. So first one, Stefan was referencing, we looked at the Alexa top million, and we're trying to determine a couple of things. Out of those million domains, what were the durations for those TTLs? What kind of sections did they fall into? And also, as Stefan also referred, where were unexpected results happening as we queried these? And so what we did was we just went and grabbed the SOA record and then compared it, and we tried to do just a dummy record to generate a negative response, an NX domain, or an empty no answer. And for those that responded with the negative test successfully, we would mark that down. Not everyone did, wildcard records and such can generate negatives across the board. And so got some interesting responses. So 2 categories here. So the TTL groupings, that was by domain, so about 1 million of those. And then also for the unexpected results, those were grouped by name servers, so fewer of those. Here's some examples of some of the results that we saw. Just wanted to really point out the categories. So a compliant server was where we would get a response from a name server where the lower between the min TTL and the SOA TTL was being used for the negative TTL. So this first one here for Vandy was responding that way, and we call that compliant. Another one where we got the low result, lower than, just kind of came out of nowhere, negative TTL, that was called not compliant low. Then the opposite, usually the case for the not compliant high, it was just using the wrong value of the 2, and it happened to be the high one. And then finally, matching. We can't be completely sure if it's compliant or not. So if all the values were the same across the board, so we just put that into its own category called matching. So here are the results of what we found just for the TTLs across the board. So about 55% of the domains responded with negative TTLs that were an hour or less. So should, and kind of looking at this just from the perspective of the authoritative server, what it's dictating. We'll talk about the recursive resolvers in a moment, how they kind of influence what that end user actually ends up with in terms of a negative TTL. So, within an hour, a lot of these domains should be recovered, but a good 45%, 44% at least were above an hour. So, this day and age, that might be a little too high. And the ones that were greater than a day, my goodness, could be a long day for those people if they accidentally delete something that they didn't mean to. Looking at the results from the expected results, what we'd expect to get back is the min SOA, or as the negative TTL. We found around 5% of name servers out there that we queried. So out of about 390,000 that we were getting responses from, about 18,000 of them responded with an unexpected value, either too high or too low. And we also looked at the TLDs that were there, and we got some unexpected high results from there as well. So a vast majority had matching, because that's usually the default in a lot of DNS software, is just whatever you set, whatever it ships with as the default SOA setting is what gets put in for all 3 fields. But we see about 40%, 37.8 are compliant, but it's the 5%, 18,000 that aren't, that's a little bit worrisome. So some takeaways from this, just a lot of domains are set for higher than an hour for their negative TTL. 18,000 name servers or so out there. And this is just from the top million, there's plenty more, I'm sure, that are out there that are responding with not the RFC expected value for the negative TTL. And the combination of these factors can make for a longer recovery time. We talk about the push and pull between having a good negative cache and then what the end user needs. And so it could be longer than you expect, and it could also be longer than is expected from the authoritative operator. That, hey, my min TTL is low, but it's actually sending out for the negative cache the SOA TTL, and so it's higher than they expect. So it could be confusion across the board here. And then, for those that feel like they might be in that situation, a possible recommendation is to set both the SOA TTL and the min TTL to the same values, and low as possible, but realizing that you're probably going to generate more query traffic when you set it really low. One more quick quick test that we did against authoritative servers. We took a production domain that we have, authoritative domain, that receives a lot of, it's a test domain, so it receives a lot of negative queries at the outset. When you see error here, that just means either empty no answer or negative or NX domain. And we tried all the TTLs on all the records were the same, the positive TTLs. And we messed around with the SOA values, the negative TTL, and just kind of saw what we got in terms of responsiveness, just to make sure things were working the way that we thought they should. And it turns out that it does, that we see a higher percentage of the responses for 15 minutes than at 8 hours. So at 8 hours, it's caching. Downstream resolvers are caching the records for a lot longer than negative answers, whereas the authoritative resolver is getting hit it more often when you have the lower TTL value there. So that's kind of what we expect to happen, so that's a good thing. Also, now we're going to shift over to some of the recursive experiments that we did. So on the recursive side, we took a validating resolver and non-validating resolver and just asked, hey, if we turn off negative caching, what's going to happen? And query load went up like you would expect to happen. So this is all just to show there's definitely good positive value in negative caching. So for the validating resolver, we saw about 20% increase when we turned off negative caching, and then about on our internal resolvers, we saw about an 8.5% increase when we turned off negative caching. So definitely clear benefits. So kind of the bigger test that we did, this was against a set of about 2,500 plus open resolvers using a monitoring tool that we have. And it checks every 15 minutes, so our data is as good as every 15 minutes. So what we do is just take a record, put it into a zone that we owned, and try various negative TTLs on that zone. And we would make sure all these open resolvers could see the record. We destroy the record, delete it, make sure all the open resolvers saw it and return to NX domain. And then we would put the record back and just ask, how long does it take until all these resolvers see that record again? And so these were the results. So we tried it at 15 minutes, an hour, 8 hours, and 1 day. And so kind of some various slices here. We, how long did it take 90% of these resolvers to recover? Well, our tool is good for every 15 minutes. So the 15-minute one responded within 15 minutes for the most part. And the max time, that can be off just by a little bit, just depending on timing between when the downstream resolvers picked up the record and didn't see it. At an hour, it took about 50 minutes to have 90% of the open resolvers recover. And one thing I want to point out, in all cases, even though it's a low percentage, it took the internet, the entire TTL, to recover, the full internet. Now, do you care about those two servers way out yonder? Don't know. But to say full recovery time, it took the entire TTL length. And then interesting too is at 8 hours in 1 day, we see 90% recovery at 3 hours. Wonder why? And so we looked at that. First off, the graph on the right there, it just kind of shows what we were seeing in terms of responses for the SOA, the negative TTL value set for more than 3 hours. You see the dip, then you see it come up to about 50% after about 15 minutes, 20 minutes or so, and that's what this graph is showing. Then at about 3 hours, it comes back up to 98 or so, and then by the end of that TTL duration, this one was a day, it had come back up to where it started. And so some explanations there, at 15 minutes, I know of one server that sets it at the recursive resolver by default sets it at 15 minutes, Windows, and there's others out there that have modified that setting to lower it from 3 hours. Bind has a default 3-hour setting, and then the rest of them come back when that TTL finally expires. So those were the tests, and so some of the conclusions, out of all this, just that full recovery time can be slower than expected. We kind of hit that one. Surprises can be minimized from the authoritative side when you take those two values, the min TTL and the SOA TTL, and set them to the same value, preferably low. We saw 5% of the authoritative servers weren't acting like you would think they would. And a possible thing that could be done on the recursive side, if a recursive server gets back a negative response and its TTL is higher than what it can see on the record there with the min TTL, use that min TTL instead. Maybe, trying to be noble. Like Stefan was saying, 1998 was a long time ago. Maybe it's less store and forward than it used to be. It's more online and right now. So having a more resilient internet is something I think everybody, at least downstream, would like, but you got to weigh that with what the load on the resolvers is. And so, what's the best balance? And the goal of this is just to start a conversation, not to say this is what has to be done, but that maybe something should be done to be able to lessen the time for when somebody makes a mistake on the authoritative side and it impacts the end user for less time. So that's all I got. Any questions?
Two questions.
Who are you?
I'm Olar Guimason from Cloudflare. If you look at the bottom of your slide, does that apply?
So I've been informed by our legal department that we need to have that there, but they're also aware that this is something that's going to be published. So
Okay.
I'm glad we're dealing with DNS and not legal issues, but
Really, really good work. I like it a lot. It's a question I'm also thinking about. And the only comment I really want to ask you on is why you're limiting yourself to mistakes. Why aren't you also talking about how long does it distribute modified information? Not just negative.
well, yeah. I mean, this special, in our case, this was kind of triggered by, we had a record, we removed the record that we shouldn't have removed, right? So if you change your record, then there is no negative TTL, where it would be positive TTL. So then you can look at Dwayne Wessel's presentation from the Phoenix OARC.
Yes.
So,
but things have changed a little bit.
yeah, no, I agree. I mean, maybe we should do some more work both on the positive and negative caching side of things.
And a quick one, any of these open recursors that you use, did you notice any of them have no cache?
Well, we only measure every 15 minutes, so we can't, in the tool we have, I don't know if we can put it more granular than that. So 15 minutes, we don't know whether it expires quicker than that or not. But I guess we could use open resolvers and test it. Okay. We haven't done that.
Benno Overeiner in Nelnet Labs. Thank you for excellent work. Very interesting. It happens that we had this discussion about this negative caching TTL last week. And so indeed, we use the SOA TTL. And so the zone owner is in control in this respect. But we're open for discussions. And if people want to have to fix this, we can fix this.
Yeah.
It's just a comment.
Mm-hmm.
Thanks.
Thank you.
See, Ed Lewis, early on you said that this is a trade-off about query rate at the authoritative server side, and I used to work in that area. I think that's not a good characterization of the problem anymore, because you allude that the things have changed, and part of that, we had set our SOA TTL to be basically the expected time until the next zone change. And we were under contract to have zones change every 15 minutes if someone requested something. And they pretty much are always requesting something. So every 15 minutes, we should have a new zone out there. So some of the rationale for TTL settings might be a little bit different. Also, and I was looking at positive results, not negative results. And we had, for some reason, I was looking at the positive TTLs we had set for some records. And I started looking at, well, do resolvers honor my TTL setting, which were higher than that for positive? And I found, no, they don't. Almost none did. And you point out that these other recursive servers do have a cap for TTLs anyway. At the time, I made a comment to some people locally, and I never acted on this, was that when I, as an authority operator, go out and set my TTLs, I'm assuming a world that no longer exists, which you're pointing out. And I think that's in general, the TTL setting discussions should be brought back. I mean, why do you set them higher or lower? Because from the authority point, I look at their RFCs and I do certain things, but recursive servers out there, and you've got a good survey of that here that's better than I've seen other places. they don't honor that. And now when I'm setting my things, I set things long and I don't want people to notice changes. But I'm getting, not honored because of this. And so that's something this is just a general, bigger problem than just what you're facing. So you're hitting a good part of it, but there's more to the same thing.
Right. Sure. Thanks.
Thanks. It was good for a presentation to get on to add. I think these days, most of the recursive software has a setting to twiddle with TTLs. And the reason for that is operators get calls to their call centers when things not resolved right. So they do things that they think is okay to get good resolution. The question I have is on the open resolver stuff that you did. Did you kind of geographically map that out and where the difference geographically on response times or on the kind of times it took to resolve?
I don't think we looked at geography. I don't think we looked at geography at all. We just looked. Okay. We had 2,500 open resolvers in that tool, and we just fired it off, and they were all over the page.
They were all over the globe, but I couldn't tell you like what the breakdown was of where they were at what time. But it was interesting. The ones that were trailing when we had the longer TTLs on there, it wasn't always in the same area. It would shift around, like the last ones to catch on that this record exists now.
Okay, so there's no kind of geographical pinpoint where there are longer or shorter TTLs used.
Right.
Okay, thanks.
Right.
Hello, Shane Kerr, BII. So it occurs to me that the cost here, while there's an increased cost on the authoritative server for lower TTLs, it's not much, right? The people who are bearing most of this cost for the desire for increased responsiveness are the resolver operators, right? So might there be a way, it would involve protocol changes, but there might be a way to actually shift that cost back to where it belongs. So have you considered the possibility of having the authoritative operators remember who they've given negative answers to, and then notify them if that answer is no longer valid? In most cases, most of the queries you receive are going to be for zones that exist. So you need to look at the numbers and see which percentage of your queries actually result in negative answers.
Right.
And it could be quite expensive. On the other hand, today memory is cheap. We have DNSSEC. You can do this in a secure way. Maybe it's worth modeling this.
So you're talking about some type of community where you can say, hey, flush this from the cache internet-wide? Is that what you're saying? Or?
Well, I have an hour TTL. I know everyone I've given a negative answer to in that hour, so I can just send them a message saying, oh, that's not, remove that from your cache.
Right. Not easy to send a message to the whole internet.
Not the whole internet.
You can try with it.
The people who I know have stale data. I can say.
Right.
Yeah.
Right.
Has this already been discussed? Am I out of the loop?
So there's a question on Jabber from Antoine, which I'll, rather than just read it, I'll try to convey his tone. So I think he's saying, this sort of feels like we're optimizing for stupid people who make mistakes and delete, mistakenly delete data from the zone. And so he's wondering if maybe, a different direction would be to improve provisioning systems to make those sorts of events less likely. So.
Yeah, it could go both ways. It's, those authoritative operators that are out there, they're not all in this room and they're not all as knowledgeable about DNS as the rest of us are. It took me coming to Microsoft and getting on the DNS team to really see, those numbers mean this. This is what the negative caching thing is all about. So there could be an outreach part of this. Hey, everybody out there that's got your negative TTL set for more than a day, do you realize what that means? They just don't know. And I think there's an education part of that. Just calling them dumb, it's not fair. They're knowledgeable technical people. They just don't understand all the nuances to what these values mean.
Right. We're going to close the mic line at the two that are standing because we've got to move on. Thanks.
Hi, Greg Jules from 3 Mobile UK. As a mostly recursive resolver operator, in the light of things like the random domain attacks, which hit us 3 years ago, 2 years ago, still are, and one of the things that we do is deliberately wind down max cache TTL to a lower value so that whatever comes back, whether it's positive, in a negative response, You know, we're going to say, you know what, we're going to flash it, whatever you've said, we're going to get rid of it when we want to, not when you say that we should. Would that sort of be general advice? So rather than leave it up to the authoritative servers, different implementations to put something other than the RFC recommends into that value, let us as the people who are consuming the information choose what we want to use.
Right. Yeah, I think so. I think the RFC recommendation there, 1 to 3 hours, and I think 3 hours is a little bit too high. That's just my personal opinion, but yeah. Because a lot of things can happen in 3 hours. A lot of calls can be spun up, and a lot of managers can get involved, and a lot of stuff. If it's 15 minutes, it's gone before the call is spun up.
So Warren Kamari again, and this is somewhat related to what Shane was saying. I'm kind of building something, which I mentioned on, I think, DNS Ops, and it made people all kinds of grumpy. A sort of collaboration server where people who have domains can go along and register this fact. And then other people like recursive operators can subscribe to a feed, like a pub/sub/hub feed. And if you make one of these sorts of mistakes, or more likely if your domain goes walkabout, you just log into an interface, you know, you've already proved who you are and that you exist, and you click flush.
Yeah.
And then it distributes it off to people. So
yeah, I saw that discussion. I think it's a good effort. I think Paul Wixie had some security related issues with that. But yeah, I think in general, I think it's a good idea. We need to, as a community, at least the big authoritative server operators and the big recursive operators have a way of communicating when stuff like this happens.
All right, thanks a lot, guys. Our next presentation is from Shuman Huck, who's a colleague of mine at VeriSign, and we'll be talking about some experiments that he's done relating to QNAME minimization.
Thank you, Dwayne. Can everyone hear me okay? All right, so my name is Shuman Huck, and I'm with VeriSign Labs, and this talk is about DNS query name minimization and also about the observed behavior of some authoritative servers in the presence of a resolver that implements QNAME minimization. So if you've been following developments in the IETF recently, you're probably well aware of what QNAME minimization is, but I'm going to do a quick review here just to make sure everyone knows exactly what I'm talking about. So essentially, it is an approach to DNS resolution that aims to provide increased privacy preserving properties to the DNS resolver. And the way it does this is that the iterative resolver, when it makes outbound queries to the chain of authoritative DNS servers, it doesn't send the full query name anymore. It strips it down, and essentially it sends only the minimum number of rightmost labels it needs to at each stage of the DNS authoritative server chain. And then as it receives responses and referrals, it gradually prepends additional labels to the query name and issues those queries to the next set of authoritative servers until it's formed the full query name. So standardization of this mode of resolution is actually ongoing in the IETF, and at the bottom of the slide, I point to an internet draft that specifies this resolution mode. And an important observation to make is that this resolution mode requires no changes to the DNS wire protocol. So resolvers can actually unilaterally implement this algorithm without cooperation from any authoritative servers or, in fact, any other actors in the DNS system. So in theory, it should just work, but one of the questions I wanted to answer was, does it actually work in practice? So here is an illustration of the minimization algorithm by means of an example. There's a more precise description in the IETF draft that I mentioned previously. But essentially, if we want to resolve www.example.com, we start at the root label, prepend the first label com, and send that query to the root servers. We obtain a referral to the com servers, add the next label example.com, issue that query to the com servers, In turn, we obtain a referral to the example.com servers, and then we send the full query name there and hopefully get an answer. So a few things also to note. If any intermediate query name results in an NX domain, we just stop resolution right there because that's how iterative resolution works. But also, this is something that may be slightly unusual. If an intermediate query name actually results in an answer, either empty or non-empty, we just ignore it, prepend the next label, and issue the query to the same set of authority servers. And if you keep doing this, you should be able to successfully resolve the name. So some variants of this algorithm are possible. So there's a proposal that involves using obfuscated or nonce labels instead of the actual labels. You could also, the next one is not really a variant as it is an enhancement. So in addition to minimizing the query name, we also tried to hide the query type also. The obvious way to do that instead of issuing the actual query type, we issue NS record queries until we get to the target zone, and then we change it to the actual query type and reissue that query. So it has been suggested by a number of people that this enhancement will be harder to deploy, mainly because of middle boxes that may not pass through NS queries successfully. And also because of a set of broken authoritative servers that don't respond or respond incorrectly to explicit NS queries. Both of these things have actually been observed in the wild. However, it may in fact be important to consider hiding the query type again. As you probably are well aware, the type of query can reveal additional intent about the communication of a user. For example, if you do an MX query, that might reveal your intent to send email to some server. If you look up say an open PGP key record, that might reveal your intent to send encrypted mail to someone, and so on and so forth. So that's something that needs consideration. Hybrid strategies are also possible. You could imagine a lazier algorithm that starts off by doing normal iterative resolution, and in the process learning the zone cuts, and then after it's learned the zone cuts, it can then optimally issue these minimized queries. So that trades some privacy for efficiency. And you could also imagine treating levels of the DNS hierarchy, especially, for example, the root in the TLDs, which are known to be mostly single label delegation centric. You could issue minimized queries there, and maybe further down the chain, you may suppose that it's a zone with not too many delegations underneath it, and then you optimally issue the full query name there. So what I did in the study is I implemented the simplest algorithm. That is just the pure query name minimization algorithm, no query type hiding, no hybrid stuff. And I tested it out on a selected set of domain names and also on the Alexa top 1,000 domains to see if I could successfully resolve their website names. I will, okay. These diagrams probably should have been earlier, but if you're pictorially inclined, this is essentially what I'm doing. Stripping labels and doing query minimization only. So let's look at an example, www.amazon.com with minimization. What we do is, in this name, there is a delegation boundary at every label. So we query using minimization. We follow 3 referrals, issue 3 queries until we get to the target zone, Amazon.com, and then we get the final answer there, and that works as expected, no problems there. However, I quickly discovered a whole bunch of domain names that do not actually work with the minimization algorithm, and the main ones seem to all be associated with content delivery networks. Many of these CDNs, the way they work is they alias the customer website name to another name in a zone that they operate, and that name, the target of the alias, is constructed in a particular fashion. Usually it involves taking the customer website name and prepending it in some fashion to the CDN operated zone name. And what happens is, in many cases, in this long alias name, the intermediate query names, they are not handled correctly. Typically they respond with NX domains, when in fact that is clearly not the right thing to do. So here's an example. So I found this quite quickly because I used to work at Penn and I tried to resolve. This was the second query I tried with my minimization algorithm and it failed. UPenn.edu, the website is aliased to this name in the Akamai CDN. So you follow, and I think it follows one or two more indirections until it gets to the actual address records. So if we try this example with minimization, what happens you see is once we follow the alias target into the Akamai zone, that's this thing highlighted in the green here, we take once we prepend the first label and issue a query, we get an NX domain response, and obviously iteration stops immediately there without yielding any usable answer. The other example I tried, which is probably relevant to all of you here, is the IETF website. And you probably know the IETF website was aliased to Cloudflare CDN sometime last year. And more or less an identical thing happens here. So let me back up a minute. And so this is these measurements I made earlier this year, January and February 2015. This example has already been fixed, and I'll tell you about what happened there in a little bit. But essentially, at that time, we follow the Cloudflare CDN. So this is how normal resolution works. Let me flip to the next one. So the same thing happens here. The first label, cdn.cloudflare.net, if we take that domain name, we result in an NX domain here, and we stop. So that doesn't resolve either. What should have happened? If we take the upenn.edu alias and we look at the target of the alias, and if we enumerate the set of query names that a minimized algorithm would have queried and look at them individually, we see that the first two, these are clearly empty non-terminal names, right? They return NX domain. And the final one returns an answer. So what should have happened for empty non-terminals is the correct answer is what? It's a no data answer. So it's a no error response code with the authoritative answer set to 1, a bit set to 1, and an empty answer section. So that should have been the right answer. So when I observed this behavior, one of the immediate thoughts that occurred to me was for these providers that provide NX domain at these intermediate names, can we actually cause resolution failure of the target name by intentionally querying the intermediate names? Because if we get an NX domain at an intermediate name, technically what that means is NX domain is an authoritative indication that the corresponding node in the DNS tree doesn't exist. That means nothing below it can exist anywhere underneath it. So I think it would be perfectly reasonable for a resolver to interpret this and cache the non-existence of all names below the NX domain boundary. So, however, I tested this out on a few popular resolvers to see if this happened or not, and it clearly didn't. Otherwise, you know, Akamai and Cloudflare would have known this fact many years ago. And it surprised me a little bit, and I found out that the actual current negative caching spec 2308, which somebody remarked was written in 1998, maybe things have changed now, but it says to do negative caching based on exact match of the query name and not by implication anything below it. So that's what it currently says, and that's what it looks like almost all resolvers implement today. But, you know, I mean, there's lots of resolvers out in the field. It's not clear to me. There may be some corner cases or some less well-known resolvers that behave differently than this. And so I don't know, do all resolvers reliably follow this spec? In my opinion, as I mentioned just now, it would be entirely reasonable to cache the non-existence of that entire branch of the DNS tree. And in fact, I came across this RFC. I think somebody brought it up in an earlier talk too. Maybe it's Stefan. But so this draft by Vixie, Joffe, and others tells you to do exactly what I just said. So I'll just read a bit out for you. When searching downward in your cache, an iterative caching DNS resolver should stop searching if it encounters a cached NX domain. The response to the triggering query should be NX domain. And when an iterative caching resolver stores an NX domain in its cache, all names in RR sets at or below that node should be deleted since they will have become unreachable. Okay, so I agree that this is the right thing to do. This is not in practice what current resolvers do. So with a minimization algorithm, resolution would necessarily stop as soon as you encounter an NX domain. That's just how an iterative resolution works. But this is also highly beneficial because it allows the non-existence caching to operate at higher layers of the DNS hierarchy, which could potentially obviate the need to do a lot of otherwise unnecessary queries. So imagine, for example, there is a non-existent TLD called NXTLD, and a resolver receives a stream of queries for blah1.nxtld, blah2.nxtld, and so on and so forth. With a minimized resolver, it only has to issue the first one, because when resolving this first one, it would uncover the fact that NXTLD explicitly does not exist. It wouldn't have to do any of these other queries. Okay, so I've had discussions with my engineering colleagues at Cloudflare and Akamai, and I'll tell you a little bit about those discussions in a bit. But I think it's clear that the big guys, will have fixed their behavior long before QNAM minimization becomes widely deployed. But if this issue is widespread amongst other DNS providers, is it sensible to consider implementing some brute force workarounds in the resolution algorithm so that we can successfully resolve them? And the obvious brute force way is to, if you encounter an intermediate NX domain, just ignore it, prepend the next label, and carry on. So my instinct is this is probably not the right thing to do. It opens us up to a whole class of additional denial of service attacks which do not exist today. So for example, I could take one of those faulty zones and ask a resolver, prepend a whole bunch of garbage labels to that name and issue it to the resolver, and have the resolver sit in a loop, constantly querying those things unnecessarily. However, I went ahead and implemented in my program the workaround anyway, just to make sure I could resolve some of these names. And the expected thing happens with the Akamai site. So I encounter two or three intermediate NX domains, I ignore them, and then I reach the target and everything works. That's this one here, right? Okay, this one here. So I ignore this NX domain, sorry, this one, right? And I ignore this one, and I get to the answer. So for Cloudflare, the workaround also works, but it uncovered additional behavior that I wasn't expected. So there's 3 intermediate query names in this alias, and the first one returned NX domain. The second one, interestingly enough, responded with refuse, and I tried all the authoritative servers, and all of them were refused. And then I ignored that one again. And the third one actually provided the right answer, no data, empty answer. And then I got to the target zone. So I talked with Akamai. So these are not their exact words. It's me paraphrasing some discussions I had with them. But Akamai's contention is that since this does not cause a problem in the real world today, it hasn't been a high priority to fix yet. However, they're working on a plan to address it and bumping up the priority. So it should be resolved, although there's not a firm timetable to address it yet. And I talked to Cloudflare as well. Again, they were aware of the defect and they had plans to fix it in the future. And I'll just jump ahead a little bit and tell you that I talked again with them in April, and this in fact has been fixed. And here's a demonstration I did a few days ago that shows that it actually is fixed. So this slide actually mentions DNSSEC. Notice I didn't really talk about DNSSEC today. The reason I mentioned that is at the same time as the fixed, the IETF website transitioned to the new DNSSEC version of Cloudflare service. And I wondered to myself, I don't know if there's any connection between these two events, the fixing of the NX domain empty non-terminal problem and the deployment of DNSSEC. Certainly in certain types of DNSSEC deployments, so if you imagine NSEC3 with pre-computed signatures, you have to intentionally install an NSEC3 record at every non-terminal. So if you're doing that and fixing the behavior, you're considering the behavior, all these things, maybe it would have been fixed anyway as a byproduct of DNSSEC deployment. But I actually don't know if there's a connection. So I was going to ask Olafur, one of my Cloudflare colleagues here, if there is or not. So what I did was, how much time do I have? Am I doing okay? Yeah, all right, okay. So I did a survey of the Alexa top 1,000 domains to see if I can successfully resolve them, and I looked at the bare domain, and also the name prepended with www. There are about 1,986 such names, not 2,000 because not everyone has a www name. And I looked up only A records as well. So here's a quick summary of the results of that survey. I had a failure rate of close to 13%. Okay, that's pretty large. Luckily, most of them are due to Akamai, about 184 of them. However, there's a bunch of other people here too. So there's Cloudflare, the Netflix CDN is here, and in Capsula, a bunch of CDNs that look like Chinese companies, CDN20, this is pretty popular, China Cache, lxsvc.cn. So one of the things I was hoping to do while I'm here is if anyone has good engineering contacts at any of these companies they would like to share with me, I could reach out to them and make them aware of this problem. Or if you'd like to help me reach out to them yourselves and do that, that would be great too. Okay, so one other thing I wanted to say is that QNAME minimization does not mean minimization of the number of queries. So certainly some queries could be minimized in certain parts of the DNS tree. However, it's not clear to me in aggregate whether queries will increase or decrease. So certainly there are larger opportunities for doing non-existence caching at higher layers of the DNS tree, and that will result in eliminating a whole bunch of garbage queries higher up in the DNS hierarchy. But on the flip side, minimization will cause additional queries issued by the resolver in zones that span names that are many labels deep. And that's particularly common in leaf zones, as we all know. And there are strategies you can employ to reduce a bunch of these excess queries, like caching delegation points and the depth of the branches that you traverse in a zone, and reusing that information to optimize your queries. But a very interesting study would be to try and measure and characterize the impact of these additional queries. So I see a line forming. I have 2 more slides, so I'm going to do those 2 slides, if that's okay. All right, okay. So, well, maybe 4, but we'll see. So here's an example. This is a leaf zone. This is the website from my former department at Penn. So here is a label that is name that is 3 labels deep in the leaf zone. So I issued 2 additional queries. Is that a big deal? Maybe not. However, it may be a big deal in some other cases. Okay, so this is the IPv6. I'm trying to look up the reverse DNS entry for this IP. Sorry, I'm sorry. The quad A and the IPv6 address got mushed together in this slide, but it's this IPv6 address here. And if I try to look up the PTR record for this, this is what happens. So I have multiple zones here that span a bunch of labels. So this is IANA, this is, this one is Aaron, I think this is 2600:/12, that's their block. And from there, this is UPenn's delegation, which is a /32. So that's 20 bits, that's 5 labels. I did 4 additional queries here. And then once I get here, this zone, because I used to operate it, I know has no delegations beneath it. So to fully resolve the name here, I have to traverse 24 labels here. So I'll give you a little bit of an eye chart in the next in the next slide. So this is what it looks like. I know you can't read it, but it gives you an idea of the ballooning of the number of queries that you might need to resolve this name. All right, okay, so what I want to do next is I would like to redo the measurements across a larger set of domains, maybe the Alexa top, I don't know, 1,000,000, 100,000, something like that. Implement the the query type hiding version of this algorithm. A very interesting study would be to take a query trace from a very large active resolver and replay the whole thing with a minimization algorithm and see what number 1, what percentage of queries fail, and number 2, what does the query volume look like before and after minimization. And I'd like to contact some of these other providers that have exhibited these problems. So this is the last slide, I promise. So I think by now everyone agrees, I think, that DNS privacy is important, and query name minimization is at least one dimension of that privacy. So some name server implementations will clearly need to be fixed. We need to better understand the impact of query volumes. And lastly, Bert Kliske, VeriSign CTO, has recently published a blog article which discusses this topic a little bit. And one of the things he brings up is that today, authoritative servers and many other organizations, including DNS OARC, of course, with the DIDL project, they make use of full query names at these servers for a variety of analytical and security functions. So if we lose all that information, we will, maybe that is the role of somebody else in the DNS ecosystem, or maybe we need to do something else. So that's something worth thinking about. And with that, I will stop and take questions. Thank you.
Okay, thank you for that. I'm Bert Hubert of PowerDNS. First, I want to apologize. The previous major release of PowerDNS 2.9.22 messes up empty non-terminals.
Okay.
Why is this a problem? PowerDNS 2.9 is the Windows XP of PowerDNS. It is,
okay.
It's refusing to die. It needs to die, but it's currently the most deployed version of PowerDNS as far as we know.
Right.
Among your list of failures of the top 1,000, I recognize at least one 2.9 user.
Okay.
I will reach out to them, but please, everyone, please do your job to help us. Tell everyone, do not run PowerDNS 2.9. It was released 6 years ago.
Okay.
A second point that, so we're working on it to make it better. The second point is you comment on, we only fixed the empty non-terminals because we had to for DNSSEC. So
No.
your guess is correct.
Okay, got it. Yeah, that was my guess.
Yeah.
I didn't know for
Yeah,
sure.
no, but
Thanks.
that's
Yeah.
why you have to fix it, because otherwise
Right.
you send out the wrong answers.
Right.
The third point about the making use trusting annex domains, that resolvers don't actually do that right now, except for the exact name. Recently, we were forced to change that behavior because the froot server in Germany started sending us truncated answers if we sent it more than 5 questions per second that caused an annex domain. This came from a server with 20 million users. 20 million users happen to generate 5 annex domains per second, or a lot more. So the recent versions of the PowerDNS recursor have a switch, which we could generalize. It's now called root annex trust. I'm looking at the guys. Yes, okay. It's called root annex trust, which means that if the root servers now tell us that this domain doesn't exist, we will actually generalize that.
Okay. Good.
And this saves a lot of outgoing queries. But for the people here that operate TLDs, we could easily expand that feature to other TLDs that actually promise, hand on their heart, that they actually mean it when they send out an annex domain.
Sure.
And it does save a huge bunch of queries. So it's actually a useful thing to do.
Okay, that's very useful. So just to clarify, so this is not a default behavior. This is by means of a switch, and it's only for the root.
Yes,
root
that's
service?
the current state. However, it is deployed in a very large telco with, I think, 22 million customers, and they report no issues with it.
Okay, great.
So,
Thanks.
Thank you.
Warren.
Warren Kumari, Google. So I'm trying to remember what the previous questioner said. I think don't run PowerDNS.
I think you're misinterpreting his comment.
So I realize that this isn't designed to decrease the number of queries, but something that would be really interesting to do would be to take the DIDL data and have a look and see, based upon the fact that you're caching, at the closest point, how much root stuff would go away, basically.
Yeah.
What the previous person
Yeah,
said.
I think
It
that's a
seems
good
like- and
idea.
it should be fairly easy to check.
Right.
Find
And we
one
should
existing TLDs.
do that experiment before everyone deploys QNAME minimization. Otherwise, there will be no DIDL data.
Hi, I'm Oliver Gummarsson from Cloudflare. Thank you for the positive report. Yes, it is impossible to deploy DNSSEC without doing this right. So, of course, you can implement DNSSEC wrongly,
Right.
but we decided not to in this case.
So you're saying it is impossible to do it. Is that what you said?
No, I'm saying that you can try to implement DNSSEC and ignore this problem, but you will not give out right answers.
Yes, I agree.
Okay.
Right. Yeah. So the thing that I was curious about is because Cloudflare does on the fly signing, right? So you could imagine an implementation where you did on the fly signing at only the edges of your zone and like not do anything in the middle, and I was wondering if that would work or not.
No comment.
Okay. I wasn't suggesting that it was a good idea or anyone do it. I was just curious about.
But my main point here is that I think we have a educational slash ignorance problem that lots of people who work with DNS do not understand the difference between an empty non-terminal and a normal name. They even deny the existence of empty non-terminals, even in their own zones when they have it. They don't just understand the concept.
Right.
It's almost as bad as when we were in the old days trying to, or still trying to fight with the load balancer writers who assumed that it was okay to write a NX domain answer to any query that was not for an A record.
Yep.
Okay. So if we want to solve this, we have to do both: talk to the implementers and also educate, because we don't know who all of the implementers in the future are going to be.
Right. I agree.
And Lewis, in your testing, do you test with a DNAME anywhere?
I do not explicitly test with a DNAME. I do not know if, so I have the raw transcript. So if I have encountered a DNAME in any of the top, Alexa top 1000.
I'll tell you, because there is a TLD that has a DNAME in it. And I can tell you which one it is offline, but it'd be interesting to test over that too.
Yeah, it would be interesting. I'll go back and take a look at my data.
Lars Lehman, I'll start off by taking a cheap shot at Warren, because this is about integrity, user integrity. And I think that if user integrity is your problem, I don't think that Power DNS is your problem. I think using open resolvers with Google is your problem. But I came here to say something completely different.
Okay. All right, I'm not going to comment on that.
No,
carry on.
It's actually a good comment, because on your last problem with the ballooning queries, the upper stages of that is going to be cached. And that real ballooning is going to happen at the lower level in the tree, where you actually have a decent chance to provision properly. So it's hopefully not going to be that big an issue, because you can actually take that hit lower down, because that's where it fans out into many servers. So I think I kind of have a hope that we can actually use this anyhow.
Okay, good, thanks.
So I just want to let people know we've got about 4 or 5 minutes before the break is supposed to start.
Kazunori Fujiwara, JPRS. Thank you for interesting presentation, and I have 2 comments. And JPTLD has many non-empty non-terminal in JP zone. For example, COJP was empty non-terminal, and now COJP has text resource record now. And next, public suffix list contains TLD structure, I think.
Could you repeat your last?
Public suffix list. Firefox, Mozilla maintains public suffix list, and it contains TLD structure, I think.
Right, yeah. Okay, thank you for that comment.
André Suisse is Nick. We are developing a Node.js resolver right now, and query minimization is a standard part of it, so we should implement it all. And the colleague who does that arrives later this week or next week, so I don't know how long do you stay here?
Sure, yeah. So I'll be here for RIPE too, so I'd be very interested in chatting, yeah. And also knowing about any other resolver implementers who have plans with this.
Okay, so we'll stay in contact.
Great, sounds good.
Hi, Dmitry at TLD. Just a quick suggestion. I loved your slide about the reverse V6, the nibble delegation. Well, I just thought in connection of the previous presentation about the what are torture attacks called. I think that's actually a great use case for a technique. And also, of course, I mean, using that to minimize traffic to reverse. And for example, say RIPE folks, I'm sure they'll be interested to minimize the traffic of reverse queries. And I'm not sure if they have any actual attacks on the reverse, like the random.
On the reverse, I don't know.
It's actually a very good use case.
I think so, right. So you're talking about the previous talk about the random subdomain attacks, right?
Yes.
So for those.
And the technique in general.
Yeah. For those, I think this may help in some situations. It all depends on what the common suffix of the attack is, right? So if you have a random subdomain that are all subdomains of an existing label, then this may not necessarily mitigate that attack. But if it is something that is non-existent under an existing one, then it will effectively screen them out. So I don't actually know what the what the nature of the queries are for the recent attacks is. So I think it will mitigate some of them, but potentially not all.
Yeah,
of
I mean,
them.
if they're trying to resolve like letters of the alphabet
Yeah,
versus let's say they pick the 64 and try to book resolve the names to find like actual servers in
Right.
that space. So then
That's right. Yeah, for the reverse DNS, right?
Right,
So
right.
you'll get various labels where you encounter nothing.
The
Yeah, you'll
dictionary
screen
in
them
the
out.
reverse labels,
Yeah,
that's of
yeah,
course.
I agree. Thanks for that comment.
This will be our last question.
So Kathy Ellman from ISC, and I liked your slide with the reverse IPv6 query, and I found myself looking at that and thinking, so if I constructed a set of queries very cleverly, then I could force a recursive server to fill up its cache rather rapidly with a whole bunch of referral information. It worries me.
True, right. Although, I mean, you can fill the cache today with lots of annex domain caching at various labels too,
Doesn't
right?
take very many queries to
Yeah.
do that.
Right. Yeah, it's something worth thinking about. Thank you.
All right, let's give Shuman our appreciation. Thank you, Shuman.
Thank you.
Okay, thank you, Sean. Okay, well, we're pretty much almost exactly on time, so thank you to all our speakers. We have coffee break now, which will be in the adjacent room and also into the foyer. So we will be resuming as per the timetable at 3:45. One quick thing I just wanted to add is that the workshop survey is now up. You can find that by clicking on the menu option for the meeting site. We'd love to hear your feedback. Thanks.
Yeah, I'll help you with this. Okay. You're gonna use that? Yeah, I guess so. How's my talk?
Hello. Now? Yeah. Hello. Welcome back to the second afternoon session. My name is Sebastian Castro. In case you don't know me, I'm the PC chair and I will be chairing the session. In case you haven't noticed, we organize all the talks in topics. So the topic for the previous session was caching. And the topic for this session is actually DDoS, which is the main theme of the workshop. And I think we have like 3 great presentations related to DDoS protection and attacks and analysis. I hope you will enjoy. But we will be starting with John on his presentation on Hedgehog. So can you?
Okay, right. So I'm John, I'm from Synodon Technologies, and we did some work for ICANN starting back in 2013 on a project called Hedgehog. And the original scope of the project was to look at the health of LRoot. But at the time, nobody had any idea what health of a DNS server meant, and possibly don't have any idea today. LRoot's quite unusual. It had a lot more nodes than any other root server, something of the order of 300 nodes. So their DSC server that they were running at the time was receiving, for example, 300 rsync over SSH connections every minute. So you can imagine that machine was grinding to a halt every minute, and then trying to use the Ploticus interface to view graphs on it was near impossible. And certainly trying to go back in time and look at what the trends were was near impossible. So Hedgehog started as a replacement for that in order for us to get to a stage where we had a system that you could more quickly and look at the data and go back historically and look at old data and start looking at the trends and start understanding LRoot's health. Since then, it's become a replacement for the DSC presenter side of things. And LRoot, LRoot has been running it since mid-2013. And they're running version 1. Version 1 has never been made public, but it doesn't have anything special in it. Version 2 is public. So what is Hedgehog today? Well, it's a new web interface for DSC data for, well, real time or at least sort of 5 minutes ago, graphing. It's powered by a mixture of R, jQuery and Google Charts. For those of you not familiar with R, it's a statistical language. And we put it in the middle of the system so that we could potentially do some analysis relating to the health of LRoot and the health of name servers in general. You have a choice of Google Charts or static PNG plots. The static PNG plots come straight from R, and they look quite nice. The Google Charts, depends on your taste, I guess. But we have recent, in version 1 that I kind of running, you have to have Flash to view some of the Google Charts, which is a bad thing. So we now have switched so that in version 2, you can choose to use SVG versions of those Google Charts and get rid of the need for Flash. One of the other nice things in it is it supports our SAT reporting. It produces YAML files on a file share for people to download. It will also do some plotting of those YAML files and covers 4 of the traffic metrics set out in the RSAC requirements. Hedgehog is also a rewrite of the consumer of the DSC XML files. So those are the files that come from the name servers or the monitoring stations next to the name servers. And they're uploaded to the main central server. And what we wrote was a C++ implementation that would take those XML files and push them into Postgres. And so thus getting rid of the DAT files that DSC used. There's a spelling mistake in the next bullet point. You can, with the tool, we made it a drop-in replacement, so you still run refile and grok just like before. And you can import XML files and output DAT files if you really want to. It says it's, oh no, sorry. You can take your old DAT files and import them into Postgres as well with the tool, and you can go from XML to DAT as well if you really want to. So this is a screenshot of Hedgehog 1. This is a Google chart. This is in Flash. And here is this thing here on the bottom provides you with the ability to zoom in and out. And if this was actually real on the live demo, you would be able to see dots moving along the graphs. And the numbers up at the top would change, and you better see what your traffic levels were. And down the bottom, this was the first stab at a node selection mechanism. When you've got over 300 nodes, it becomes a bit difficult to decide how you're going to select the ones you want to view. ICANN already had the concept of regions for each of their nodes, so we stuck with that. And there are buttons to select the whole of one region, deselect the whole of one region. You can deselect everything and then just select one node to look at the data for. There are ideas afoot to make that more usable, maybe regular expressions. So you can say, I want all the nodes beginning PRG, presumably those are in Prague, or maybe a tree structure for looking at them. This is one of the static plots. So this is a PNG file produced directly from R. And in this case, we give the users the opportunity to choose between a stacked linear log or linear graph. They obviously each have their benefits and drawbacks. So Hedgehog 2, this is the public one. There is a demo that you can try now. I did just turn the Postgres limits up to 200 connections, so hopefully you won't crash the system, but I bet you can if you want. It's beta 2, and it has some important improvements over version 1. Traffic volume plots are now faceted. I'll show you an example of that in a minute. There's new traffic query response difference plots, and that's to do with the RSAC stuff. Somebody who I don't know personally has added vagrant provisioning. So you should be able to spin this up, I believe, in the test environment. We've improved the configuration of the system quite a lot. And we fixed a smattering of bugs, but I wouldn't want to say many. And the release candidate of this should be out soon, like in the next couple of weeks, not months. This is an example of one of the faceted plots you can get. This is showing the number of queries and responses by transport and IP version. The red is the queries, the green is the responses, and it's faceted according to UDP, IPv6, UDP, IPv4, TCP, IPv6, and TCP, IPv4. Most of the time, you'd expect the number of queries and responses to be exactly the same, in which case all you would see mostly is green overwriting the top of the red. So I had R just introduce a little tiny bit of noise into the positioning of the red graph, just so that you could see that it was there below the green one. There are places where you see differences, and that might become apparent on another slide. One of the things that we think causes there to be occasionally a different number of queries and responses is the DSC data collector forks itself every minute. And so if the response, really? Oh dear. If the response comes out after the minute that the query was in, then I guess that would be a mismatch, Dwayne. This is another similar plot showing just the difference between the two. And you can see that it's mainly small spikes and noise around 0 that you're seeing in there. Hedgehog 2.1 will be the next release after this one's gone. We're going to have improved TLD monitoring. We're going to make use of R to analyze the data and start learning what is normal and healthy. We're going to support the non-traffic RSAC metrics, add geo reporting, and one of the other things we need to do is packaging. If anyone in this room is a Debian type packager and wants to give me a hand in the bar, I'll buy them a beer tonight. I've started packaging it for Debian. One of the requirements of ICANN was for it to run on Ubuntu. And so it's only been tested on Ubuntu, currently 10.04.02. Future enhancements, more statistical analysis of the data. I want to make the web interface more of a dashboard type interface rather than just static plots. We are going to be adding a data access API for 2 reasons, one I'll come to in a moment. And we want to test and port it to other platforms so that lots more people use it. And currently only supports Postgres. Maybe the one true database, but we think a generic database layer would be a good idea. Data collection. Currently DSC consumes the currently Hedgehog consumes the DSC generated data. But we want to write a replacement for that DSC collector, and we want to make it usable for all environments, including those where you don't have an out-of-band network and you don't have port mirroring or something listening in on your network, and you have to, like LRoot would have to run it on the same machine as the name server. So the collector will have to be able to do things like resource management and throttle itself back in the event of a DOS attack, because although you obviously want to see what's going on, at the same time you don't want your collector helping the DOS attack. And we want to move some of the data processing out onto the nodes. Most of the time, most of the nodes are probably fairly idle, and they could do a little bit of processing, maybe maintain a little bit of state, perhaps do a 24-hour aggregation of the data, that kind of thing. We want to add the facility to drill down to PCAP files so that you can click on some weird peaks and go and get the PCAP files that produce them. We want dynamic configuration. We want to have a standard data model for data collection. And I have written a draft on the subject. It's only been seen by a couple of people so far. It needs a lot of work, but there will be one hopefully soon. It will be open source. It's on Apache 2 license. And the collection will work on FreeBSD and Ubuntu in the first instance. So yeah, we're open source, beta 2, Apache license. There's a website, DNSstats.org. It's hoped that will become an umbrella organization, a little bit like the original OpenDNSSec setup, so that the community can contribute code or money or whatever in order to get more of the stat stuff done. And the code is on Hedgehog, is on GitHub, if anyone wants to get it. And some more pretty screenshots there, who do bar charts. That's showing a place where you can actually see in real data there that the number of queries is bigger than the number of responses. I only got that graph this morning. I don't know why that's happened. And there, the differences, again, you can see the difference between queries and responses is quite large. 300,000 in the middle there of UDP IPv4. But that's out of 3.6 million queries per minute. So, and that's it. Oh, one other thing, Anand earlier this morning said it took 300 packages to install. We just did a test install, it was 104, and that included the fact you had to develop, build from source as well, because it's not packaged yet. So it had all the development libraries in it. So hopefully it's less than 100, well under 100 dependencies.
Hello. How are you doing?
Good.
So we stole the idea of using those charts, those stretchy band charts, off Eric Vinke, because they look really good. And like you, we think Google Chart API is good. It's a bit weird.
Yeah.
And I noticed they've been saying for about a year and a half, if you depend on this flash chart, as far as we're concerned, that's zombie code. And their SVG is the only one they're prepared to carry forward.
Yes.
So if you're cutting code now, I wouldn't bother putting anything about the flash in. I would only use their SVG version of
I
the
would
rubber
recommend
bandy
the same
chart.
thing.
That's the first thing.
Yeah.
Second thing.
Actually, one thing
yeah.
just to say is on this, the SVG version of this chart, if there isn't enough room for the legend, it just overruns end the line. It doesn't wrap.
Yeah, well, I mean, why would you care about that, right?
Well, if you've got 300 nodes, you care.
Yeah, but I mean, from their point of view, I mean, it's flash.
Yeah.
You didn't expect it to work.
No,
anyway.
this is the SVG one.
Oh, the SVG one.
Yes.
Oh, well, in that case, that should be fixed yesterday. That's
Well,
shocking.
there is
Can
an
you put the
open
bug report in? I haven't got time.
There is a bug report in, and it's being ignored.
Damn.
Maybe somebody from Google.
No, that doesn't work. I've tried that.
Oh, okay.
So the second thing, I don't have a problem with R. I mean, I think R's fantastic. It's what real mathematicians use for a living, people like quants and things like that.
Mm-hmm.
But did you have to use R? I mean, really?
No.
Because you're not doing complicated stats.
It's not at the moment. All it's really doing at the moment is acting as an interface between the database and the graphs.
Oh, okay. So it's data management because it will talk to nice backends.
Yes.
All right.
It's got a DBI interface. So.
And the last thing, all my buddies who looked at the Google chart crap said, you should use Diamond D3. You should be on D3. D3,
Yes.
D3, D3,
Yes.
D3. So I'm saying to you, D3.
I had another slide on that. So very
I've never used
subject.
it. I don't know if it works.
Saying that I wanted to use D3 and have R just upload the data to JavaScript. My project manager, business partner, and wife, sitting at the back of the room, forbid me from going straight into the design details and not talking about requirements.
I'm done.
Martin Levy, Cloudflare. You mentioned it's open source, and I was just trying to bring up the GitHub to have a look at this. Only TLDs? Could we use this for non-TLD data as well?
Yeah. Basically, it's the same as DSC. So if you can use DSC on your systems, then you could use this.
But you've only focused on TLD stuff, so
yes.
When I look at the source
root
code,
stuff,
root stuff.
mainly,
So I can
and
look
TLD
at,
stuff.
I can change that.
Yeah.
And it's open source.
Yes.
Thank you.
And there's an issue thing on GitHub as well. Feel free to file issues if you find them. We'll try and fix them quickly.
And on a separate note, yeah, don't bother sending an email in on fixing charts at Google. I'm with George. I've given up.
Yeah.
Hi, John. Jim Reid, just a computer programmer from Scotland. Boring question. Is ICANN paying your company for the ongoing maintenance and support of this software?
You would have to talk to ICANN about that, I think. Fair to say. Terry Manderson's the man with the money.
Yeah.
And we'll have to see if the contract gets renewed.
Okay.
I mean, some of what I've talked to you about today is funded, some of the features that I talked about. But there are plenty of features that aren't funded, if anyone wanted to fund them.
Yeah, the reason I'm asking is that DSCMG appears to be put on the back burner by the very nice people at CZNIC who are looking after that software. So if there's a need for a presenter interface or something like this which can present the data, maybe there's a need for something which has got a little bit more behind it in terms of active support.
Yeah, I mean, that's the aim of the DNS OARC, is to come up with something like OpenDNSSec had, with multiple organizations within the community contributing to the development, design, and funding.
Okay, thanks. Cheers.
Anyone else?
No, yeah, that will be the last. We are past on the time. Thank you very much for your presentation. You are. What? No. Window. No, that's the other one. Yeah. No. It was a PDF, right? Yeah. But I don't see it. Because it's this one. Yeah. All right. So the next presentation is from Marek, talking about DNS packet flood Marek Pachkowski? Almost. Almost, okay. And from Cloudflare.
Hello, I'm Marek Majkowski from Cloudflare. Yes, I will be talking about the DDoSes that we see on Cloudflare. There is plenty of material in the world about how DDoSes, how the random prefix floods look from the recursive point of view. There is some analysis how they look from TLDs, although not too much. I don't think there is much data about how DDoSes look from the alternative servers provider's point of view, so let's hope you will find it interesting. The presentation is roughly created in kind of 3 parts. One, I will talk about most about network mitigations, which I'm afraid will make you sad because that's mostly about how we drop packets. Then it will be more about dropping packets, and then finally, how do you automate dropping packets? Don't worry. It's only the approximation. It's just the scale. We do answer some packets, but in comparison to what's on the inbound is pretty much 0 or close to 0. All right. So the problem is quite large. Everyone is kind of affected by the problem. All the major names of DNS providers are or were affected. We are one of those. Just to give you a comparison of what we see on a daily basis, this is a kind of normal graph of packets per second on inbound, outbound. You can see that kind of inbound is a bit smaller than outbound. We are doing some other traffic as well. That's kind of the kind of silent day. That's kind of the normal day when the inbound is just gigantic compared to outbound, and that this all inbound is packet floods against our servers. So it's, I don't know, 20, 30 times more than the kind of baseline, or even more. To give the scale, I know that people are asking about numbers. We daily see, on daily basis, we see 100 million packets per second hitting us. Sometimes it's more, but then we lose visibility. So it's kind of the upper bound. We have no idea. 100 million, I definitely have numbers for that. So we are alternative DNS provider. We have name servers, and if you're our customer, say example.com, you will be allocated 2 name servers, in this case, Paul and Emma NS. And I'm kind of putting that here to make it explicit. Those 2 name servers will likely be flooded if you are the targeted domain. So it's the name servers for particular domain that are being flooded. We mostly see DNS requests as for port 53 UDP, and they tend to be heavy on the packets per second side, so on packets. We do see SYN floods also against DNS servers, but for some reason they tend to be heavy on the bytes per second, so there are spikes in bandwidth basically. Interesting nitpick, we did see a few times kind of hit and run attacks when there was a big flood against DNS infrastructure on UDP. So packets, and then a few seconds later, or overlapping, there was a big SYN flood against the same IPs. So basically, if you're using SLIP or use a truncation bit to ask your recursors to come back over TCP, that may not work just because you will be SYN flooded in the same moment. So what we do on network side? Well, network side is all about the scale, all about capacity. So basically, when anyone sees more traffic flowing in, then there is network. There's pipes, basically, network capacity, and the only thing you can do is null route or buy more ports, but that kind of takes time. As Cloudflare, we are very lucky because we also serve some other traffic, not only HTTP, so we have some spare capacity. If for us, network is not that a big deal. We are quite well done on that. So the only thing that you can kind of control is the network topology. We are running an Anycast network. We have many POPs around the world, and that gives us few advantages. One advantage is that we can null route IPs locally, so we can say that this name servers are not available, but only for these locations on these providers, which is very powerful for most of the customers, or for a big part of customers. It's okay for them to only be served in Asia or in Europe because they don't have too many customers in other parts of the world. So sometimes that's acceptable. The other thing that Anycast gives you is if there is a big problem, if one data center gets flooded heavily, all that would be local. And finally, if normally the traffic is spread nicely around the world, so we don't see that many packets hitting a single colocation usually. The topology on the DNS side is also, not totally stupid. We have name servers allocated and done in that way that we can totally survive null routing of 2 name servers. This will affect the targeted domain, so the DDoS will be successful, but it will shield other customers. Other customers will not see any impact. I know that other DNS providers have similar infrastructure as well. So basically, it's all to survive null routing of 1 or 2 or few IP addresses. But if you are a DNS provider that has few name servers, not a large number, then then you're in a very bad position. Very harder to defend. The new trend on the floods that we see for the last few months is it's quite interesting. So normally we see a flood against a single domain and against usually a pair of name servers. But since a few months we see floods hitting many domains at the same time. So the flooders basically do know that they want to hit particular website, and these domains are usually very similar. They only change with a number or something like that. And I think what's happening is the website owner is informing its users we are likely to be flooded, so therefore our service is likely not to be working. So if you cannot access, say, foo.1, foo01.com, please try foo02. Maybe that will work, and so on and so forth. Which is good kind of from the UI point of view, I guess. And then on the HTTP layer, they are all forwarded to a third domain. But from the authoritative DNS provider point of view, we get many domains flooded at the same time, which is problematic. So basically, be aware of the way you allocate name servers to customers. And then if that actually can reach us, if it doesn't cause congestion, then we are using some tricks on routers, mostly ECMP, to just spread the load across more than one server. So ECMP allows us to basically direct a single IP address against many servers. That works like charm, so highly recommend it. We also use FlowSpec for firewall rules. I'm not a fan of FlowSpec. I will say later on why. FlowSpec is not very granular. You can only drop based on packet length, which sometimes is good. But on the other hand, in other cases, you can be more specific. And it doesn't work with the random length floods, which happen very often. But FlowSpec is quite easy to deploy, so that's why people are using that. And finally, at some point, the flood will hit the DNS server. And I just want to kind of point out here that the number of packets per second that can be handled by each layer is kind of different. And DNS server is actually quite slow here. And the reason it's slow is just because networks on kind of generic computers is slow. You can do at most double-digit 1,000 packets per second on a single core on a single server. So if you have heavy optimized DNS server, you can do, I don't know, maybe 300,000, maybe 400,000 packets per second, and that's the upper bound. You cannot do more on a single machine. And if you compare that to the number of millions of packets that hit us, it's kind of a lost game. And it's important to understand that just because receiving packets in the application is so slow, it kind of makes little sense to do much smart things in the application. Because since you receive the packet, you might just as well just answer it. There's no reason to not answer it. We did have some more complex things in the application, our DNS server, but they weren't too effective anyway. And pretty much the only magical thing that we do in the DNS server is we never bind to kind of star, we never bind to 00 to all the IP addresses on port 53. And the reason for that is the shared receive queue. So if you were bound to kind of star 53, then you will have a single file descriptor, a single receive queue for that, for port 53. And if you see a flood against a single IP address, this flood will go into this receive queue, will fill this receive queue, and the packets to other IP addresses will not have space. So what we do instead is we bind to every single IP address specifically, which basically makes sure that there is this receive queue for each IP address, which kind of limits the damage during big floods. As I mentioned, just because the DNS application, the DNS server is slow, people are discovering other ways, some ways to shield the application from excess of packets. And people are rediscovering IP tables. IP tables usually traditionally can do only kind of fixed offset matching, but they can look at the payload. The router cannot look at the payload of packets. U32 is well known, but what we found is the IP table BPF module. We found it to be great. It has bytecode, so it's quite cumbersome to use, but it's very fast and it's very powerful. So with BPF, we can actually do better packet parsing. We can almost parse the full DNS packet. And the speed it gives us is about 1.2 million packets per second per box. If you optimize your IP table stack nicely, you can do about 2 million maybe. But still, it's slower than what you expect from the router. So the TCP dump, so BPF is based on TCP dump. So if you've never heard about BPF, BPF is kind of the core of this presentation. So that's the takeaway. BPF. So BPF is known from the TCP dump world. So if you ever wondered what happened when you type TCP dump with some expression, this expression gets compiled to a bytecode, and this bytecode gets passed to the kernel. So the API between TCP dump and the kernel is this bytecode magic. It's not Turing complete, but you can have quite, there is quite a bit of programmability there. And BPF is in the kernel is now being spread. Originally it was only TCP dump, now it's being used in other use cases. It was implemented in IP tables quite recently, because in 2013 only. Yep, and originally the tools were quite scarce. So yeah, it was quite hard to use. So to work around that, we implemented our own, maybe not compiler, but kind of parser to BPF. So here you can see example of two command line outputs. The first one is creating a rule, a BPF expression to drop or to match packets that go to star.example.com. So you can see some assembly bytecode here. If you like assembly, that's quite cool. If you don't, then I don't know, don't look here. Anyway, I find it quite cool that you can actually, it's kind of like assembly. You don't have loops because it's not Turing complete. But anyway, you can quite specifically say what you want to match on. What you want to parse, and then at the bottom you can see the output of the compiled bytecode. If you don't want to start the assembly, that's how it looks like. What you pass to IP tables. The tools we are using for that are open sourced, and they can do various kind of basic things what you would expect, like match on star, or match on 2 characters, or 1 to 4 characters of prefixes, or be case insensitive, or match packets that are not DNS at all. So things like that, the kind of obvious patterns. So let me argue why. So now we know how to kind of drop packets in IP tables. Now let me argue why this is actually correct, which is actually a good thing to do. So let's kind of generalize, and let's say there are roughly 3 categories of packets we see on our authoritated DNS server. So one is the normal traffic, like people using DNS recursors, using Google records or something, and then the recursor asking us the auth for data. Normal traffic, nothing fancy. The second type is what people usually call the random prefix floods. When the botnet or some other malicious actor, doesn't matter, asks questions to real recursors, but asks with random prefixes, and the reason for that is to forbid recursors from doing any caching. And then those recursors pass on this request to authoritative. So from the auth point of view, those requests are valid. They come from real recursors. But the users behind them are not really real. It's a botnet. It's not a valid user. And the third category is just packets straight flooding against us with spoof source IPs to make it harder for us to distinguish they are bad. But basically they're flowing directly without any recursor in the middle. The good thing to do for all this is kind of different. So for real traffic, we obviously should answer. For the indirect floods, ideally we should answer not to upset the recursors in between. And for the spoof packets, there is no point in responding to them at all. Like it just doesn't make any sense to respond to packets that don't come from real recursors. And the important bit is that the number of affected users by kind of dropping on each layer is inversely proportional to the size of the flood. So the real traffic is really tiny and affects every real user, the kind of the real traffic. On the other hand, the spoof traffic is gigantic and it affects exactly no one because it's not real packets, it's not real requests. So the whole magic is to kind of draw this line and be able to drop things as close to this kind of high volume spoof packets as possible, while not upsetting the real traffic and maybe even the indirect recursors. So you may ask, okay, but how do you know which traffic is real? Well, the answer is sometimes quite simple. If you see a literal question mark in a label, most likely this doesn't come from real recursor. If you see a literal comma in a label, and by the way, the comma delimited domains are actually right now being flooded, it may also be an indication that this packet didn't come from a real source. We see literal HTTP, we see 2 subdomains, 2 random labels, in which case we are likely not an authoritative provider at all for this domain. We see also the kind of fixed domain, fixed queries floods, in which case, again, it's most likely spoofed, because if that was real, it would be cached. So if we see a big high volume of www.foo.com requests, it is most likely, like 99% are spoofed. The only question is with the random prefixes, when you kind of do or don't know whether they come from recall source or not. It's a bit harder to see. So for most categories, it's quite obvious which packets are spoofed. And even if you cannot tell by looking at the DNS query, well, you cannot tell whether the packet is spoofed or not, is fake or not. There are some other vectors you can use to select based on those packets. You can use, if you're using Anycast, as we do, you know which IPs are original, which are not. You can also do whitelisting of IPs. I know that many people do whitelisting of the well-known recursors. There are some other correlations you can find in packets. So basically, it's all about kind of the managing of the impact of what you drop. So in the extreme case, if we see a random prefix flood to start.example.com, on the right-hand side, you can say we drop everything, all right? Then it affects all the customers. It affects the customer. It affects this domain, and basically it makes the deal successful. Sometimes this is what you want, because sometimes you're not authoritative DNS provider for that domain, or sometimes the domain has moved from your servers. So sometimes this is actually what you would expect. Then the kind of a bit better case is dropping all the prefixes except some whitelists that you know are actually valid domains, like www or mail or ns1 or something. And the rationale here is it should not affect real traffic too much, just because real traffic doesn't hit NX domains too often. So basically, the real traffic should flow normally. It's only the recursors being used as vectors that will suffer, because they will mark your DNS servers as down because you don't answer to the random prefixes. So you may want to mitigate that as well. You may want to add some rate limits, and then the flood you will only punish the heavy recursor that hit you heavily. You will not punish the lightweight recursors only used as with small packets per second. So only used to some extent. But that's a big discussion to have, whether if your customers are using recursors that are being used as a vector in a flood, then is there anything you can actually do in the authoritative side? It's like the recursors are kind of being used in a flood, so they are busy asking the random prefixes under random queries anyway. So is there any point in responding to them at all? They are busy anyway, so the customer experience is awful anyway. But the point is, you can kind of slide this. You can choose as you wish. And in the perfect case, you would just answer all the queries coming from your recursors and drop all the invalid ones. And that's totally feasible as well. The volume that we saw of the random prefixes coming from real recursors was relatively small. It was totally manageable. So this is a possibility as well. So as I mentioned, the IP tables in Linux are quite slow because network stack in Linux is, well, as it is not as I would expect, let's put it like that. So what we are doing is we have a kind of a module to offload the IP tables processing to user space. We are using kernel, we are using Solarflow and network cards. And we are using kernel bypass to basically run the BPFs faster in user space. So during a big flood, we just spawn this process in the background. It's runs in user space. It claims a part of traffic, and then it runs our BPF rules with way higher throughput than normal IP tables, and that works quite well. The only disadvantage is that it uses one core because it does polling. It's proper kernel bypass. So it can do about 6 million packets per second per box using only one core. The accuracy, so kind of from operational point of view, accuracy takes time. So if you now route an IP address, all you need to know is IP address, which is not too much data. On the other hand, the kind of deeper you go, the more specific you want to be, the more data you need to gather in order to mitigate it correctly, and that takes time. So in the Cloudflare history, we kind of evolved from just nulling to being more specific when we are right now, and we are just starting to roll out the automation and kind of centrally managed things. The pain is definitely increasing, so we definitely need to make big progress on that because it's becoming unbearable. So this is packets per second over the last 30 days. I'm not sure if I can say that the trend is growing, but definitely both the volume over time is growing and the frequency of the floods is growing. So for us, there is no other way than automate everything. So right now we have semi-automatic system, which still needs a human operator. We collect samples from switches, the S-flow samples those are real packets that go to a central system that analyzes them and tries to recognize patterns of the floods that we see and prints that to an operator. Operator then reacts to that. So this is an example of the kind of the analysis output, what operator sees. You can see IP address. Yeah, redacting that was fun. You can see IP address. You can see some patterns like what is on the network, and then you can see some millions of packets per second during this flood particularly. And then the operator can react with our central IP tables management tool. And the syntax of this tool is pretty similar to the previous one. So you can basically mitigate based on patterns as you choose. It was done deliberately so that the operator can pretty much copy and paste particular floods as he wishes. Oh yeah, there is by the way the comma delimited flood at the bottom. So they do happen. We are working on optimizing that. We are working on adding the automation layer in the middle. It's fairly early days. It's basically a hierarchy of simple transitions of the kind of the flood metadata with some parts decorate the flood. But yeah, the kind of the summary is that time to mitigation is critical to basically limit the impact on innocent customers, and you want to be as selective as possible. And there's no other way than dropping packets, especially if you know they are actually spoofed. And automation is kind of a process that is still ongoing. It's not a single project. Yes. Thank you very much.
Thank you, Marek. We have plenty of time for questions, so please shoot.
Kathy Almond from ISC. You stated that for the large recursive server operators that you didn't think that it was correct to squash their packets. I wonder if it might be better to actually stop responding to them so that they know that there is a problem.
So I don't think there is a problem. So it's for our scale, we can totally afford answering the volume of packets coming from your recursors. The problem is, can we distinguish the spoofed ones, so the bad ones, or not? And I will be very explicit that it doesn't make any sense whatsoever for us to answer the spoofed packets because the volume is just gigantic. And even if we could send 100 million responses per second to the internet, that will have no value whatsoever.
Jelte, SIDN. I saw that slide about what you decide whether something is spoofed on. And I was thinking for the very first one already, there's a question in there. I think that's an actual resolver.
It is possible, but then you're totally right. But then it won't be seen in my tools, which only show like hundreds of thousands of packets per second.
Yeah,
because
of course. If you see this
cached.
100,000 times per second, then probably not. But okay, but it's this sounds like somebody actually typing that in a browser that doesn't do any checking. But my extra question would be that if you don't answer resolvers, if you just drop it, then they'll just gonna ask again and again and again.
Unless they are smarter, in which case they will have some fallback mechanism. They will mark me as down, which may or may not be what I want. Sometimes I do want them to stop. I'm not too afraid about that. They can ask me whatever they want. The volume of that, they are using CPU as well, and their CPU is limited as well. So
but that's the reason that RL does truncate packets once every 50%, I think, by default, instead of just dropping everything. So I was wondering if you had considered that as well.
Yes, but
oh, okay. Sure. Thank you.
Thank you.
Thanks a lot. Great talk. I'll definitely like to talk to you about what resolvers should do to the authoritatives. One thing, I mean, are these the actual numbers that you're seeing? 100 million packets from spoofed, and the rest is kind of below million?
Yes.
So it's actually not a problem that, well, normal resolving does have, or it's a...
well, it is possible that the normal resolving traffic will hurt our application, our DNS server. It is possible. We haven't seen that yet. Yeah, for now, I wouldn't be too worried. So basically, as long as the resolver has some sane rate limits, like don't send more than 1,000 or whatever, a number, then that's fine. That should be okay. That should be acceptable.
But you haven't seen any kind of difference in the resolvers sending a certain rate or going above a certain rate?
In most cases, for most of the customers that are being flooded, it makes little sense to care about this about the open recursor. So even if we drop the open recursors, yes, the part of users that will use that are relying on open recursors will suffer probably. This is an acceptable. Sometimes it is acceptable loss for us. So yeah, what was the question? Did I answer the question?
Sort of. I mean, I was just thinking because one of the next presentation is most of the resolvers now have these outbound rate limited. So I just was curious if you saw a difference over time in recursors giving more or less traffic.
No. Yeah, it's quite flat for us.
Okay, thanks.
On the global scale, yeah.
John, I can. I just wanted to know, when you were looking at IP tables, did you look at U32, and was there a reason you chose one?
Yes, definitely. I even have a slide on that I kind of skipped. The U32, the problem with U32 is it's quite cumbersome to use. So this is an example of a rule. It has more limited matching. So here you can kind of. You cannot do dynamic things. You can only look at it's fixed offsets or fixed offsets shifted by some value in 1 byte, which is very cumbersome to use. On the other hand, in the BPF, I actually can write a rule, as is here, that actually parses the packet. So it doesn't have loops, so it's not full parsing, but it's way more, it's easier to use, it's more expressive, it's nicer to write. So U32 overlaps to some extent, but I prefer BPF.
Okay, cheers.
Hi, Bert Hubert, Power DNS. First, thank you very much for sharing all this knowledge. This has been very educational, and I realized that you don't have to share this with the world, but it's appreciated that you do. First remark I want to say is when you get queries from reflection attacks from resolvers, where you rightfully say, well, we might as well answer them, those questions, it's in fact very important that you do. Because some resolvers have logic that if you stop answering questions, after a while they will declare your whole IP address dead to protect you.
Sometimes this is what we want.
Yeah, sometimes that may be what you want, but it will impact lots of other domain names as well.
Very much depends on the use case.
Yes, but it's appreciated that we get an answer from you, because it indeed saves us keeping a lot of state and otherwise declaring your server dead.
So I think it's a discussion between the recursor and the off. Sometimes the off may want to save fallback. Sometimes the off would like to keep the recursor to actually work. I think the whole model is pretty much broken. So if we assume that there is an attacker that can flood recursor, we are lost anyway.
Yeah. So I understand. Maybe it's hard to do standards work in DNS these days, but if you would send us a packet, please shut up, we would shut up.
Definitely. There's plenty of room for improvement. Definitely, it would be nice for us to say, like in the presentation of earlier today, that for the example, the NSEC negative caching, that would be very, very interesting, because then we could push back. Then we say, oh, by the way, for this particular domain, we will give you the NSEC response. Therefore, you should cache it more aggressively. So it would be nice from the protocol point of view to be able to shift the responsibility for sending NX domains basically upstream.
Yeah, we would appreciate that. The other thing I'd like to mention is, like you, many of us have run into the issue that UDP on Linux is needlessly slow, to the point that we did a benchmark on TCP/IP and it was actually faster than UDP. This should never happen.
I can believe that totally.
Well, the reason it happens is because people do all their benchmarking on TCP/IP.
And the other reason is that contract is on UDP kind of makes no sense. So.
It makes no sense at all. But since we all run into this issue, people are now running UDP stacks in user space. You're running the UDP stacks in user space. Everyone in the DNS community is sort of staring this in the face. It might make sense to one day talk to the Linux kernel people and say, well, can we find some way? They implemented a whole set of UDP standards for Goldman Sachs for high frequency trading. They might as well do something for DNS.
So I did try in this presentation to make it explicit that the volume of real traffic is reasonably small. So we are not too worried about answering those packets from the application. We are totally happy to drop them in IP tables or another some faster way. So I don't really, it doesn't make much difference for the DNS server itself to be able to answer. What we care is the IP tables being faster, at least what we care.
Okay. I think the discussion quickly gets complicated, but I hope you'll be around later today or tomorrow. Thank you.
Hi, excuse me. My name is Roy Adams. I work at Nominet. I initially had 3 things, then I had 2 things, and then I'll stick with 1 because most of the stuff has been answered. Well, really quickly, I noticed you mentioned the floodgate. Have you guys looked at Solarflare network cards?
We are heavily relying on Solarflares.
Oh, fantastic. Yes. Okay, so that's 1. Number 2, really quick, if you want to distinguish spoofed traffic from real traffic, one of the things that stared us in the face for a long time was the IP time to live, the IP hop count. It's an interesting indicator if you want to do something interesting with that. Lastly, just a remark on an observation we had recently, well, a couple of years ago, which is interesting if you want to do something with it. There's a fundamental difference how resolvers behave, and of course this is about dropping packets, so this might not apply to you, but there's a fundamental difference how resolvers behave when they don't get a response or when they get a slow response. For instance, when they don't get a response, they become very aggressive. When they get a slow response, they're going to be very, very nice. They're going to leave you alone. So for instance, if you want to do some maintenance or some management on your set of name servers and you don't have the ability to just shut down the pipe, you still want to respond, right? What you can do is respond slower. So all of the important resolvers that are well configured and well behaving and their server selection algorithm now migrate to your other set, and you can do your maintenance on this one. It's just an observation.
The disadvantage is that then you need to keep the state of request for longer. But yes, I'm
true.
sure there are many ways, many tweaks we could use to have this discussion with the recurser to basically express what we actually want. Ask us more questions or not? Don't ask more questions or.
Perfect. And thank you, by the way. This is brilliant. Absolutely brilliant. Thank you.
Thank you. Thank you very much.
Excellent. Thank you very much, Mark. That was a really good presentation. Thanks for the questions. We ran 10 minutes of questions. That's great. So switch. No, you're not knowing.
Okay, so I just go to full screen when I'm ready.
Yeah.
And then I also want to browser like that.
Ah, okay. Was Firefox or was no? That was Chrome. Oh. Yep. No. Stiff. All right. Now to continue, we have Matt from VeriSign, who's gonna present about what VeriSign does for DDoS and handling of large volumes. Can you just switch screen?
So thanks, Merrick. That was a good presentation. A lot of what Merrick said really rang true to some of the things that we do every day. My name's Matt Weinberg. I work at VeriSign. It's my colleague, Pete Barber. And we work on the team that's responsible for operating ComNet and ANJ-Root and a bunch of other interesting things. I wanted to start off the presentation just by showing our real-time HUD, our heads-up display. We don't typically show this, but in the spirit of trying to show and discuss as much information as possible, we start with this. This is showing real-time within 10 seconds the number of queries per second we're receiving for all the products that we serve. This is ComNet, Root, our managed DNS service, other things all combined. So each box represents one of our edge sites that we have, and you can probably figure out some of the locations of these boxes based on the names. You can see AMS1 there in the middle is Amsterdam. So here we are. We'll speak a little bit to these points and later in the presentation, but I just want to start with that and just showing you that. So give me a moment here. Okay.
So what do we do? Most of you pretty much already know this, but I thought I'd start by telling you what we do. We are authoritative for com and net, which at today's number is about 130 million domains. We also operate a couple ccTLDs, including .cc and .tv. And then we also are authoritative for domains like .jobs, .gov, .edu, and a bunch of other ones as well. We're also one of the 12 root operators, so we operate both A and J root. We also have a DDoS mitigation platform that we offer to enterprise customers. We have a managed DNS service for those who want to offload their DNS to us, and then we have a recursive DNS product as well. So uptime, uptime, uptime. Our corporate communications group loves advertising our uptime. We have over 17 years of 100% uptime running .com and .net. If that number ever resets, look for Pete and my resume. But hopefully it will continue to stay that way. And we typically do about 110 billion legitimate DNS queries a day. So we have 17 large points of presence around the world. That was represented by each of those boxes that you saw on that heads-up display I showed you. Those sites host all of our products, and they have access to both Tier 1 network providers, and we also do peering as well there at those locations. And then we have a bunch of small regional sites all around the world. Right now we have 69, actually I think we're up to 70 and growing. And those only host ComNet and JRoot only. And I know there's a few of you out here that actually host some of those nodes. We can talk about that a little bit later as well. So I just quickly wanted to plot all the points of location on the map. It didn't really turn out the way I wanted it to. The green points represent our large mega sites, we call them. And then the red dots represent those small regional sites I told you about. So we want to talk a little bit about some of the things we do with regard to building our infrastructure, and we'll also talk about some real world attacks. Of course, we have to design for maximum uptime. I showed you that tweet from our corporate communications group. We have to have the ability to sustain large attacks. You saw that we were receiving about 1.2, 1.3 million queries per second. We can do that on 1 or 2 servers, but we have to be able to handle that query load times a much bigger number. So we have to build for that. And then of course, performance is always a consideration as well, trying to reduce latency wherever possible. So build big, build wide. The advantage, of course, is it gives us lots of breathing room when we are under attack. Of course, the big disadvantage for that is that it's resource and financially intensive. And sometimes the bad guys want to use us for reflection attacks as well. Speaking about our network capacity, right now we're at about 2 terabits per second worth of network capacity, and that's constantly growing. We also operate our own dedicated backbone that's installed in most, but not all of our edge sites. That backbone, we have peering relationships with 700 networks and at about 1,400 points of interconnection. Currently, about 80% of our traffic is served via peering relationships. And by doing that, we can not only improve or reduce latency, it gives us added network diversity, but we can also do some fun things on our backbone with regard to filtering and traffic shaping and other things as well. Server capacity, again, we have to build for big numbers, so we fine tune all our servers to be able to handle many, many queries per second, and then we have lots of those servers. We load the ComNet zone completely in memory, serve it out of memory with our own custom database, and we tune for bare metal for some services, and then other services we can virtualize more easily. So there's a lot of things we have in our Swiss Army knife tools to basically do mitigations. We have in-house developed software on our load balancer stack, our name servers themselves. We can deploy filters on both the load balancers and the name servers. We have a heads-up display, which I showed you at the beginning of the presentation. And then we've done a lot of work on the Linux kernel for tuning purposes, basically eking out every clock cycle we can out of every server to respond properly. We can filter at multiple layers. We can filter at our core routers. We can put ACLs in place when needed. We use BGP FlowSpec and QoS as well when we want to. We can make sure that a certain level of traffic can be allocated to a certain service. with our own custom load balancers, we can do all kinds of fun filtering. We can filter based on packet size, query type. We can put filters in place for rate limits. Basically, if you can isolate it, we can filter it. And we can even do that on our name servers as well. So we can do the same filtering on our load balancer layer or our name server layer. We also have a storm cluster that basically ingests SNMP, real-time SNMP data, NetFlow data, a bunch of other things as well, and helps us basically generate filters when needed. And so that's kind of in line with what Merrick talked about and what they do at Cloudflare. Our proprietary name server is highly tuned for what we do. It reports real-time statistics to our heads-up display in the order of about once every 10 seconds. So we always know what's going on within 10 seconds of an event. And then we can filter, again, based on packet size, query type, anything really we want. So now I'm going to hand it over to Pete Barber, who's going to talk a little bit about attacks.
Good afternoon. So we receive a lot of attacks, and I'm going to boil this down into 3 different categories of the attacks we've seen. So we have a couple of options when we do detect one of these attacks by using our HUD or having any sort of other tools to alert us of traffic events. We have the option of filtering the offending traffic, and if the attack is big enough, we can start isolating the attack between sites so that some sites will be less affected than others. We also have the option of isolating the traffic within the site, and we can dynamically allocate more servers to handle the traffic, or we can move the servers around as we need to. As I mentioned in the last slide, we can dynamically allocate resources with many of the tools we've written between our physical sites, between our bandwidth and our circuits, and we can always filter at the appropriate layer, whether it's load balancer or the name server. One of the options that we really have to consider is that filtering is not always the best solution for a traffic event, and we'll talk about that in the next couple of seconds. Sometimes when you do a block of all the queries coming from legitimate name servers, you're going to get a bunch of retries. Sometimes the attacks aren't really big enough for us to do anything about, and really response rate limiting is going to be our go-to tool for most of our attacks that we have coming up. So one of the attacks we've been seeing most recently is these random queue name reflector attacks, is what we like to call it. So one of the notable ones happened in August 10th of 2014, where we, in 2 separate events on that day, received 2 different queries. These were, I'm sure you recognize things like this. I'm sure everyone in this room has already seen these, but in this case, we saw 3 million queries per second, first for the JD7777.com and later for the LT8005.com. The pool of IP addresses that were hitting us with these queries was about 135,000 /32s, and of those /32 addresses, they were coming from 96,000 /24s. After the fact, we did a spot check on the IP addresses, and we found there was a good correlation between IP addresses that were hitting us with these queries and ones that were listed in the Open Resolver project. Conclusion is these were real name servers hitting us, as opposed to something being spoof sent to us. So in this case, ComNet normally doesn't see these sort of attacks because of caching. In this circumstance, we saw both of these because the domains went NX domain, and there was no delegation for it to go to. And we saw these a lot higher rates than we normally would see. Sometimes root servers also see these random queue name attacks, and it's usually done when there's a typographical error done within the queries. Like if someone does a literal period in a TLD that is being queried for does not exist. So this is what happens when you filter one of these attacks that happens from real name servers. This chart, I'll go into details on the next slide, but there was a ramp up. We filtered it. The filtering, you can see the difference between the black line and the blue line, and the queries actually exploded from 3 million to 14 million after we put the filters in place. So zoomed in, we have normal traffic rate was about 2 million queries a second during that time of day on that day of the week. And then the random queue name event started, and that was shown by arrow pointing to number 2. That was the first ramp up. We put the filter in place, and then the queries went from 3 million queries a second to about 15 million queries a second. So at slide number 4, that was when the attackers decided to change their query from the jd777.com to the lt8002.com query. And the caching name servers out there didn't have to retry anymore. So they went back to the 3 million queries per second. Then we put in the second filter, not really realizing that was what was going on. That day when it was happening, we thought, oh man, they immediately ramped up the attack. No, it was just, it was name servers doing retries. And then after a while, they gave up at number 6 here. The attack went back to normal traffic levels for the day. But I don't want to talk about that. So the big sites fared pretty well, but some of our smaller ones, as we talked about, we have 17 big sites and we have lots of little smaller sites, and they don't have quite the same level of transit or peering network capacity. And the BGTLD servers net is the one that we have that's widely unicasted for that, and actually it showed up on RIPE, on the RIPE DNS monographs. So we learned a couple of lessons about filtering, and that's if they're real name servers, it's much better to rate limit them than to just simply drop them. So a caching name server can do a 4 times or more retry. So if you're going to drop attack traffic that's coming from real name servers, you're going to have a bad time. So the lesson we learned is don't filter drop 100%. Do a rate limit drop if you can. If you can't rate filter it, then what do you have? If you don't have response rate limiting available for you, you can't really ask caching name servers to stop that because of the source of IP address is 135,000. You can't write emails that fast. Yeah. Another option we thought of but haven't ever tried before, may or may not work for you. If you're a TLD operator and you have the ability to add and subtract zones in this circumstance, that might have helped us out. If we could have, it was already NX domain, or else the traffic wouldn't have been coming to us. But if you have the option within the policies of your TLD to add the domain temporarily and offset it to a set of sacrificial name servers, then that'll help you defer the traffic off to some other name servers. They won't hit you and there won't be any retries. And you don't need any of our fancy VeriSign Atlas filtering software. The second class of attack we saw, I'm sure everyone in here may already be familiar with this. This is the reflection attacks, which was coming from forged IP address sources. Those forged IP address sources were hitting us, and we would send large responses. Usually they were Apex name queries, but we also did see it sometimes at the VeriSignLabs.com name servers. And the reason they chose that is because there was a big, healthy size DNSSEC enabled response for the Apex query or for VeriSignLabs.com's DNS query, especially if eDNSSEC was turned on. The IP address usually came from a small range of IP addresses, and we suspect that they were trying to blow up someone's website by bombarding them with lots of DNS responses. I'm sure a lot of people in here have already seen this. Bad guys had a good payoff, 32 bytes in, 2,000 bytes out. That's a pretty good deal. It's pretty hard to track down because the source addresses are all forged. And we had a lot of load capacity, and back when these were happening, we didn't have response rate limiting in place. We also, in fact, found the code that does this on Pastebin. I may be able to share that with you if you're interested, but it's pretty dumb. The attack was in style around 2013. We haven't really seen it since then. If you've ever seen one of these packets, and I don't know about you, but I can read TCP dump, and I mean this is a very recognizable section of a small DNS query. It's only 32 bytes in size. This is the Apex query for .name, and there's something about this that makes it different than any of the normal traffic that comes into a name server, and it's this section that I have highlighted in the blue here. So there's no name server out there that legitimately uses a 9,000 byte eDNS zero buffer size. And if you can isolate that part of the attack, and we did, and you can put an IP table as U32 rule in to pick up that section that I have highlighted there, you're just going to kill the DNS attack traffic from these eDNS 9,000 queries rather than what's legitimately coming from name servers. We used this IP tables rule pretty effectively during the events that were happening in 2013. And the third class of attack is what I call a ZZ.com style attack. And it wasn't necessarily ZZ.com that was always being it, but the domains always seemed to be the same. They were always some sort of gaming sites internationally, usually Asia. And in this case, we were being used as a reflector. And it was our best interest to filter this as quickly as possible. Rate limiting is also a pretty good response here. What we think is maybe the bad guys were doing this exploit in order for somebody to take out the domain from the TLD. I'm sure it just wasn't us that were seeing this type of attacks during this time frame. If you filter 100% on it, maybe the domain that was in question is now offline, and that was the goal of the attacker. Future plans? Matt will take this part.
I know we're running low on time, so I'll try to be fast here. It's just a few slides. Talking about what we want to do in the future, of course, we're always in the market to increase both our network and server capacity. We have to build to the worst case scenario, not the everyday scenario. We also are trying to increase our deployments of those regional sites I told you about. I know there's a few operators here that actually help us out with that. If you're interested and available to host one of those servers, there's the URL, or you can talk to Pete or me anytime. So RRL is something that we've been implementing, and it's something that's gradually changing and ever evolving and tuning the knobs and everything else. But it's something that is an important tool for us in terms of stopping attacks. Something that we're really excited about is leveraging the Intel DPDK toolkit and also FreeBSD NetMap to basically take advantage of, say, a 10 gig card in a box, bypass user space, talk directly to the network card. And by doing that, we can, on a single server, handle about 6 million queries per second of legitimate traffic, which saturates a full 10 gig pipe. And by doing this, we can add diversity at our load balancing layer. We don't have to just use dedicated hardware load balancers. We can now use ECMP to balance traffic between the load balancers that have a bunch of back-end reels and also servers that really announce right upstream using DPDK, basically that technology, and allows us to do even more capacity. So that was it. We really, when we started doing this presentation, we were wide-eyed and really excited about doing this, and then we realized there's no way we can do this in 30 minutes. So we went fast here, and just our goal was really just to share information, and we'll take questions now.
Microphone is open. No questions for Matt or Pete? I guess that's a no. Oh, thank you very much, guys. Really Thanks. Lovely presentation. Ralph, you're up too. Oh, there we go. I have to sleep. That's yep.
Yep.
Okay, so this is the last presentation from this block. We are running really, really well on time. So take things easy, Ralph, if you want to. So the last presentation comes from Ralph Weber from Nominum, talking about analysis of DDoS data from their platform. Hopefully it will be really interesting. Ralph, the floor is yours. There we go.
Okay. Well, thanks a lot. I'm still baffled by the Cloudflare talk, which kind of had a different, I mean, I thought we were seeing lots of data and lots of abuse, but it looks like others are seeing even more. So I talked about this topic a couple of times before, and this is in the beginning sort of an update. In 2014, these attacks were really kind of like pushing the limits. And what you see here is a graph of the numbers of unique names that we see on, or our customer sees on their resolvers. And that really spiked up to an unbelievable number. That's the different random name prefixes there. And in 2015, this actually has flattened, but the flat line is still a lot above the 60 to 80 million legitimate names that people ask around in the internet. So it's not really quite. What we've seen, and we begin to categorize these attacks, we've seen different randomization algorithms, and we've seen different sort of traffic patterns. Some of them are from some hosts, but with a high query rate, and others are really with low query rates and with lots of hosts. But in the end, they give the same attack, the same result. They attack the authority and try to take down the authority so that people can't go there. And the use of OpenResolver still is a lot. I mean, the number has gone down to, I think when we started looking at this, it was 26 million. It's now 17 million. Some of this might be because people now block inbound port 53, which of course then the scan also can't see them anymore. But these are still used more for the stealthy attacks, I think, these days. Another attack vector that we saw are bot-based attacks. This is quite the opposite. So people using devices that they have there, and this can be sometimes even a surveillance camera or some other thing that runs some form of Linux that is easy hackable, and then they use that and fire as much queries as they can get to the recursors. Recent example of that was Rutgers.ego, was I think 1 or 2 weeks ago happened, and regardless which way they take, I mean, they've caused a lot of stress on the DNS infrastructure and on the resolvers, on the authorities, and we've been talking about this for quite some time, and by now I think most of the vendors of DNS software have done something to mitigate against these attacks in their software. And there's, of course, rate limiting outbound to the authoritative is one thing that I think the IC Bind recently implemented, and others implemented before. And the other is, of course, ingress filtering, because if you drop the traffic right when you get it, there's no effect on anything else in the DNS world. So I was just curious on how good these results were and what the actual result for a user were if we would kind of either have normal traffic or have traffic to that domains that are attacked. So I built myself a little setup which has a resolver. I mean, it's not an ISP resolver, it's just a setup that I've made. And then this gets normal traffic. The normal traffic is something that I've sort of collected from a customer resolver, cleaned up a bit the data so that we only really have good traffic, and then run against this. You will hear some more about that a day in the life on Resolver tomorrow from my colleague. And then sort of apply the filters that the various softwares have and see how effective they are. And with that, I did test Bind, PowerDNS, Unbound, our implementation, Venture Kashref. And to actually kind of do that, I had an authoritative server that had a rate limit. I initially thought maybe having 2 domains and having different rate limits made an impact. I found out it actually didn't, because the rate limit, we'll see later, then when the domain sort of goes, the results go bad, they go bad so much that it really doesn't matter if your rate limit is 1 QPS or 100 QPS. So I had that set up, but it made no difference. And then, of course, the normal user traffic will get 100% of the replies. So the normal traffic I sent didn't hit the rate limit at all. And then when I insert the attack traffic, of course, it overflowed the rate limit. So more details, the server hardware, kind of some beefy machines with 10 gig interfaces and 4 gigs of internet connectivity. I used DNS Perf, which tool some of you might be familiar with, to actually run that traffic, as well the normal as the domain traffic. So I made 2 DNS perfs. One actually ran at 10,000 QPS, which had the sampled customer traffic in, and one that ran at 100 QPS that just had asked the 2 domains. So 99 questions for the domain with 100 QPS and 1 for the domain with 1 QPS. And then I used TCP replay to insert the attacker traffic. And the attacker traffic were basically 5,000 QPS for non-existent names, one for the 1 QPS and one for the 100 QPS domain. So the total was 20,000 QPS, which, as said, shouldn't be a problem. It wasn't a problem for any of the implementations. My the idea was not to do a performance test of some idea. It was really just how effective in the normal operations, because you all run your DNS server at, say, so that you have lots of headroom. Because if you don't, then there are always new attacks. There are always news attacks out there that kind of can hit you. And the test run then ran for 15 minutes. That's just the time, because I didn't want to spend too long waiting for them. And I did a couple of runs to, first to preload the cache, so I didn't want to see the impact that maybe the empty cache had, and also to rule out problems that I could have at one point in time. But all the results were fairly kind of similar to this. Now, this is running over the internet, so packet loss is expected. So there were low levels of packet loss that I didn't have concerned about. And if you think about the authoritative server that I set up for this test domain, it was one authoritative server with one NS record. So as soon as the packet is lost, you're out of luck. So I wasn't concerned about low levels of packet loss or server fails and that kind of. And of course, then after the test, I count all the packets and then did two together. So the high performance setup was in our company headquarters in Redwood City, and I have a small private server that I run my stuff on that I just used as the authoritative server for that. And luckily enough, they were fairly far apart, so you also have some impact on the latency of the query. Because in a lab, if you have something like next to each other, it just answers. And that's not how the normal behavior is in the internet. Stuff just takes time in the internet. And then, of course, the first thing I think, I run the good traffic, and the results is a log scale. So don't be too concerned about the other stuff. No error and NX domains are valid answers. The traffic that I collected was actually, everything was no error. And I then did cleanse it twice so that I really got all the NX domains up. And the next day I run the traffic, well, I got NX domains. So that's just the way the internet works. So NX domain wasn't a concern. And the lost packets also were below 100 out of the, I think it was 9 million or 90 million packets. So it wasn't a big concern to do that. And that was the one stream that ran the user traffic, as I call it. And then there was the other stream that had much less packet because it was running at 100 QPS. That's the test domain. And with that, so one thing, please delete out of your memory everything you see with Unbound there. Because I was puzzled a bit initially why this is the case. And I had some exchange, and I sat together with Wouter just before that presentation, and we figured out what the problem in my test data was. So it's not a thing with Unbound, it's a thing in my test data. And I did a test by changing the test data a bit that then produced the same result with Unbound as the other service. So the Unbound numbers in that presentation are a bit high, but I will rerun all the tests and then upload the presentation with the changed numbers, because the other numbers look pretty much in line with what I saw. And then, of course, as said, most of the result is okay, no error, and we see some server fails that are caused by packets being lost, but it's saying something in the 100 range, so out of 100,000 packets, that's not too much of a concern of. And on the authoritative server, I then look what I've answered, and I've answered for most of the questions no error, and as I said, forget the Unbound numbers, so these are wrong there at the moment. And I've then collected also some system stats of that, so that's not exactly, I think, there's some, the amount of cores that were, oops. Did I do something?
Go out there to view.
Can I do that? Nope. Sorry.
Oh, this one is like that. No, you change the zoom. No, it's not. This computer will restart in 5 minutes.
Not sure if I can be finished in 5 minutes.
What is that?
I have no idea.
Why is that?
Looks like it's lower now, which also should be okay.
Yeah.
Okay. So these are the statistics that the CPU that the different servers use during that normal time. So, I mean, all of them, I mean, this machine had something like 40 cores. So even if, I think it doesn't correct totally, but the maximum use was something like 12 cores. So there's still lots of headroom for all of that. Then I mean, ran the attack traffic and to see if what would happen if there was no protection. And that means basically I ran bind because that's just what I had available without the outbound protections. And I could see that there was an impact in the real user traffic because that's real user traffic. So that's traffic that was sampled and then users normally would expect no errors. And without the protection, we see, I think 15 to 16% of serve fails. And again, these log scales, that's why it's a bit off, but the numbers, and I'll have the exact numbers in the slide later, were something like 16% were serve failing. And that's something that's noticeably, I mean, every 8 query of a user would basically not result in what it should have been. So I think that is something that would have been felt by a user. And that's, again, the attack traffic was still low volume compared to other stuff we have seen. And if I now switch on the outbound protection, which I think PowerDNS and ourselves have by default, and with unbound and bind, you have to configure them, and then run the user traffic again, I see basically much the normal user traffic is protected. So outbound protections to authoritative servers work to protect users from other traffic. So unless you're the attack domain, these outbound protection work very well. Now, and I mean, I can flip forward back between the good traffic and the protected attack traffic. There are some variations there, but it's really, really minor. Keep in mind that this is a log scale. So it's, okay. And now look at the other results. So now we run the attack traffic and tested the attack domains result. And you see there, it's the total opposite. So most of the traffic for the attack domain gets answered serve failure. It was between, I think, 96 and 99% of the traffic. So if you are the domain attacked and the ISP only has the outbound filter, the attacker actually achieves what he wants, taking the domain down, at least for this ISP. Because you can't go there. I mean, there's a 1 in 100 chance that you'll get a good response back. And of course, if you filter on the ingress by just having a black and a white list, which I think you can do with multiple implementations, I mean, I just did it with ours, then the authoritative server only gets the sort of good traffic, so the responses that he's get back is also the good responses. And as I said, if you compare that now with the traffic from the test domain with the good traffic, you see it really flips over. And on the authoritative servers also, I mean, as I said, my authoritative server can't answer as good as Cloudflare's. So, but I observed that under attack, the no error answers are really, really minor there. I see a couple of them that answer no error. Most of the traffic that gets through with the outbound rate limiting is the attack traffic, which still is okay because you only reserve a certain kind of amount of traffic which you can handle, but which still is kind of a lot. And another thing you see, again, forget the unbound numbers, although unbound kind of also nearly handles the maximum amount of traffic, the dropped traffic is a lot lower. I mean, I haven't that on the slide here. The drop traffic without protection was something like 2 million queries that were dropped. And so if the outbound rate limiting works, it's something like 80 or 60,000 traffic that is dropped. And again, it's if you compare that now to the good traffic, flip back and forth, you see it's kind of the opposite of it. Oops. Yeah, now the machine reboots.
You can take a break, Ralph.
No, well, I can do the sum up of that. I think is pretty clear. So, outbound rate limiting works. It's great to protect your normal traffic that's not the attack domain. Outbound rate limiting doesn't protect the attack domain. So if the basically attacker wants to take down the domain within one ISP or within your resolver framework, it doesn't help. You need to do ingress filtering. So ingress filtering, if the slides come back, I'm going to explain a bit how that works for them. Allows you to only send the good questions to the authority and drop everything else, which I think I think it's similar to what the people at Cloudflare do with the IP tables. They just when they have the when the domain is can you log in now?
The presentation.
Do we know the password for the presentation account?
Password
1, 2, 1, 2, 3, 4. No, that's Ralph hasn't finished. So we need the password for that for the presentation account and not computer.
Where's Paul? Dinesh has it. I don't have it.
Do we have a whiteboard?
Or blackboard, chalk.
Yes.
Yeah. Apologies for the interruption.
Oh, there he comes.
Run, Dinesh, run.
Yeah. No, Dinesh, you also do not know the password.
Pay attention to the password.
We need someone.
Let's make some white noise to cover the password.
Shout it.
Yeah, it was all going too well.
Yeah. Yeah, this is the point when you notice the workshop are running so well with something like this. It's like, oh, come on. How you dare to do that? Tin, 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 tin. Now we'll have a beach ball.
Awesome.
Open recent PowerPoint.
Yeah, I'm going to try that.
Still rebooting?
No,
No, we haven't.
we're trying to load now.
Updating font menu.
Shall we just take his?
Yeah.
What's
I'm gonna find it. No worries.
Okay.
Just take this and
Do you know audio?
let's hope it works. Where is it?
Let's give it up.
So where is the presentation?
And it's
Do you have the video feed?
Yeah. Okay.
We're back in business. Excellent.
Great. Okay. So yeah, this will just the system stats for the protected traffic. As you see, the amount of CPU is a bit higher because it's twice the traffic, and it's also some stuff that the recursor have to do outbound. But again, it's way below the threshold of the machine. And these are the numbers. As I said, I'm going to correct the slides with the new unbound numbers and upload it later so that you can actually see what the exact traffic were if you want to reproduce the result. And here, I've done the takeaway. So ingress filtering works for protecting the domain. Outbound filtering works for protecting your other user traffic. And just some stuff. I mean, there was an attack last week on Apple Daily.com Taiwan, which was actually an interesting domain because it was so widespread that the amount of queries from one participating host was so low that we nearly missed it. So but in total, it was a lot of queries. It was something like at the sample we had was 735 million queries in 40 minutes and 10 million clients. So that's a lot. And compare that to the other attack we have, I think last week was Rutgers Edo, which had more total queries, but a lot less attack clients. And I said much more QPS per attack client. Now to the rate limiting, I think that's roughly what the Cloudflare slides were also showing. If you have to whitelist legitimate queries. In that case, for Apple Daily was very easy because the random attack queries were prepended to the www label. In that case, it's easy. You basically pretty much block everything before the www label, and then whitelist the www to actually resolve. And that leads to www label being protected because you can resolve it. Everything before it will be blocked, and everything that is kind of outside that domain tree will resolve normally. And I think that's a good way to handle these queries with an ingress filter. Of course, over time, the attackers will change and adapt, and your whitelist might have to become bigger. But I mean, that's just the way the world goes. There's nothing you can do about it. So with that, I mean, summary, we see a lot of these DDoS attacks. I was amazed to see what we see or what I don't see at Recursor, where I think I saw a lot, but it looks like the DDoS attack that is not using any recursors are even bigger. And I'd like to speak to people from the authoritative world about what we can do to maybe make the relation from the legitimate to the authoritative better. But I think so far, dropping and then rate limit dropping seems to be the way we go. I'm not sure if others will agree. And yeah, I mean, we try our best to get the users the best results. So with that, I'm up for questions.
Question won't be interrupted. So please. Don't hurry, Bert. We have time.
So, well, thank you for doing the measurements. We've also been doing a lot of these measurements, but sadly, most of them have been in production.
We have some production measurements, but I can't share them.
Well, actually, I can. That's the nice thing about being open source. What we have indeed found is that the attack patterns shift a lot. So we keep seeing different domain names, different targets, and we also see that these attacks, they start and stop at very synchronized times. So they're actually attacks for rent. So there's an economy behind it. Yeah. We also tried to figure out if there was anyone controlling those attacks. And we discovered that almost all of these attacks come from home gateways and reflections and that kind of stuff. And that the IP addresses of the attackers are very constant. So within a service provider environment, if you have 1 million customers, typically your attacks will be coming from 5,000 people, maybe 10,000.
Yeah, I mean, these are usually the open home gateways in the resolver. But I mean, even these within providers often change when the networks are rebooted.
They do. But the interesting thing is, so we asked our users, we said, well, if you know who these users are that are attacking you, because they're your customers, they pay you money, you know where they live, you have a cable that goes to their home. Why cannot you ask these people to clean up their gateway? And then they told us, well, for one, we gave them the gateway, so we feel sort of bad about it. But the other thing they said is, well, contacting a customer costs us in the order of €100 or $100, and then we help them clean up their computer or their gateway, and it typically helps for a few months. So they said there's little we can do because the economics of being a service provider, which means that you make a few dollars or euros every month, mean that we cannot afford to contact the people that are attacking us. And we spend a lot of time pondering that. So what can we do based on this knowledge? Because we cannot simply disconnect these people. They will call the service provider and generate even more cost that way. So what we finally figured out is that, and Pete Barber also mentioned this idea, let's configure a few sacrificial name servers. Where we say, look, these are the name servers for the people that run open relays. These are the name servers for the people that are infected with botnets. And we have the list of IP addresses that are currently attacking us, and we put them in our load balancer infrastructure or whatever. And all the queries that attack us, they go to those servers over there. We had to do something with this Pentium 2 that we had around. And this means that those people will be attacking their own name server. It's like a sort of Anycast at home, where you have these attackers and they're only soiling their own nest. And we found that even as IP addresses change over a provider, this is an optimum that you have these attackers. You don't have to shut them down. You don't have to disconnect them, but they will only be attacking their own name servers and getting inferior performance. But the thing is, these people were already running computers with 25 pieces of malware on it. Their PCs weren't that fast anymore. So that is a solution that we have found in addition to the egress measures we've been taking. And I can recommend this to anyone. Should you be around tomorrow, we talk a bit more about this in the DNS dist presentation at the end of the day. But this is my tip.
I mean, we've suggested the cleanup to our customers also, and some of the customers came back, well, these are our business customers. We can't actually, and we can't even run them to bad servers because they pay us a lot of money. So
we had the executive said we cannot insult our customer by contacting them and telling them they are infected.
Yeah, it is. Yeah, it's a sad truth.
Yeah, that's how it is.
Yeah.
Thank you.
Thank you.
Any other questions for Ralph? You want to go to sleep? Go for beer? Okay, that will be it. Yeah, we're really good, well on time. Thank you, Ralph. Sorry for the disruption. So that is the last presentation for this session. Just a little message as a PC chair. We have the survey for the workshop available. It's in the workshop webpage. Please fill it up. We use it for actually improving our criteria for selection of talks. So if you're considering, oh, the talks have been really good, it seems the program committee is doing a good job, help us to improve that work because we account the survey results and also our internal process of selection of talks. And that's it for me. Keith, do you need your slides?
Okay. Just a few announcements before we finish. Can you social slide up? Sorry, what? There's a social slide, if you can find it.
Should we switch or?
Okay. So, for the social tonight, it's at the CCC Music Cafe, which is basically you go out the hotel, you turn right, you head right about 2 blocks, and then you can see it just on the right. About, I think it's the second or third on the right. You can easily Google it, and I think we have a slide which will show you where it is. Please bring your badges. That's how they know that you're people that they're to give drinks to, as opposed to anybody else that might be in there. PGP signing session tomorrow. We've set up an alias PGP sign at dnsoarc.net. Please, can you send your, if you're participating, please send your public keys to Matt via that alias, and he will build a key ring which we'll put on the website. We will probably use the Meerman room, which is opposite the elevators, the lifts for that. We restart at 9 a.m. tomorrow. Before we finish.
Do you need anything from here?
Yeah, somewhere there was a slide we did which had social information on it. I'd just like to thank our sponsors again. Yeah, that's it. I probably need to put it in slideshow mode. So a big thank you to SIDN for being the gold sponsor and also for tonight's social. VeriSign as the other gold sponsor, Comcast as our silver sponsor, Nominum as the bronze sponsor, and then ZRS as our contributing sponsor. So social starts at 7 p.m. So you basically got an hour and a half to chill out. Thank you all, and see you all at 9 a.m. tomorrow. Off you go.